Welcome to your journey toward an enticing career path in the data science field. Data science has witnessed recent marketable growth due to the abundance of electronic data, computing power, advancements in artificial intelligence, and its demonstrated business value. In the United States, the U.S. Bureau of Labor Statistics projects a 35% growth rate in the field. Currently, the median annual salary is an estimated $103,000. So begin your journey into this thriving and fascinating field with this course. Its increased adoption across industries has fueled demand for skilled data scientists who can use data to tell compelling stories to transform and inform businesses. In this introductory course, learn about these opportunities and investigate the needed career skills to become a data scientist. Additionally, this course will help managers and executives who want to learn about the field to help transform their organization to become more data-driven. This course is designed for beginners, so you don't need prior knowledge or a degree in data science or programming. It serves as an introduction to the field. Take this course if you are curious about data science and how and why data science is transforming our world. Learn about concepts such as big data, different branches of artificial intelligence, and how data science leverages these ideas to uncover and tell hidden stories. This course is the first in several other specializations and programs, including IBM Data Science Professional Certificate, Introduction to Data Science, Key Technologies for Business, IBM AI Foundations for Business. You will meet several data scientists who will share their insights and experiences in data science. You will have a foundational understanding of data science through instructional videos and videos with data science professionals, readings, practice assessments where you can practice your skills, glossaries for your reference, and a video that summarizes each lesson. At the end of the course, you will have a case study and a quiz based on it as a final assignment. You explore data science job listings in the final peer-reviewed project. Let's take a more detailed view of the course content. The course is divided into 3 modules plus an optional module. In the first lesson, you'll explore what data science is, the data scientist's role in an organization, and what makes a skilled data scientist. Then you continue this module by learning about what data scientists do. You'll also learn essential skills for becoming a good data scientist and why significant data matters. You'll explore handling different file types, study data science topics and algorithms, and discuss the qualities that define a data scientist. In Module 2, Lesson 1, you'll explore the interaction of big data and cloud computing in driving digital transformation. You will also learn foundational concepts, key tools, and data mining techniques essential for data scientists in this dynamic landscape. In the second module lesson, you'll dive into exciting concepts of artificial intelligence and data science. Throughout this module, you will explore artificial intelligence concepts like machine learning and deep learning, gaining valuable insights and skills. In the third module, you'll embark on a journey to explore the vast and impactful realms where data science plays a pivotal role. This engaging module delves into various activities that shed light on the diverse applications of data science today. In addition to these 3 modules, you are also offered an optional module if you'd like to familiarize yourself with data literacy concepts for data science and where you will learn about the data ecosystem. Topics include sources of data that data professionals use in their day-to-day tasks and distinguish between databases, data warehouses, data marts, and data lakes. You gain a basic understanding of how data gets processed, such as the extract, transform, and load (ETL) processes, and working with data pipelines. While participating in this course, if you encounter challenges or have questions, you can find support and answers and connect with other learners and support staff in the course's discussion forums. And now, welcome to the course. We look forward to you completing this course, earning a valuable certificate, and continuing your path to a data science career.
Data science is a process, not an event. It is the process of using data to understand different things, to understand the world.
For me, is when you have a model or a hypothesis of a problem and you try to validate that hypothesis or model with your data.
Data science is the art of uncovering the insights and trends that are hiding behind data.
It's when you translate data into a story So you use storytelling to generate insights. And with these insights, you can make strategic choices for a company or an institution.
Data science is a field about processes and systems to extract data from various forms, whether it is an unstructured or structured form.
Data science is the study of data, like biological sciences are the study of biology, physical sciences, it's the study of physical reactions. Data is real, data has real properties, and we need to study them if we're going to work on them.
Data science involves data and some science. The definition or the name came up in the 80s and 90s when some professors were looking into the statistics curriculum, and they thought it would be better to call it data science. But what is data science? I see data science as one's attempt to work with data to find answers to questions that they are exploring. In a nutshell, it's more about data than it is about science. If you have data and you have curiosity and you're working with data and you're manipulating it, you're exploring it, the very exercise of going through, analyzing data, trying to get some answers from it is data science. Data science is relevant today because we have tons of data available. We used to worry about lack of data, now we have a data deluge. In the past we didn't have algorithms, now we have algorithms. In the past the software was expensive, now it's open source and free. In the past we couldn't store large amounts of data, now for a fraction of a cost we can have gazillions of data sets for very low cost. So the tools to work with data, the very availability of data, and the ability to store and analyze data, it's all cheap, it's all available, it's all ubiquitous, it's here. There's never been a better time to be a data scientist.
Everyone you ask will give you a slightly different description of what data science is. But most people agree that it has a significant data analysis component. Data analysis isn't new. What is new is the vast quantity of data available from massively varied sources. From log files, email, social media, sales data, patient information files, sports performance data, sensor data, security cameras, and many more besides. At the same time that there is more data available than ever, we have the computing power needed to make a useful analysis and reveal new knowledge. Data science can help organizations understand their environments, analyze existing issues, and reveal previously hidden opportunities. Data scientists can use data analysis to add to the knowledge of the organization by investigating data, exploring the best way to use it to provide value to the business. So, what is the process of data science? Many organizations will use data science to focus on a specific problem, and so it's essential to clarify the question that the organization wants answered. This first and most crucial step defines how the data science project progresses. Good data scientists are curious people who ask questions to clarify the business need. The next questions are, what data do we need to solve the problem? And where will that data come from? Data scientists can analyze structured and unstructured data from many sources, and depending on the nature of the problem, they can choose to analyze the data in different ways. Using multiple models to explore the data reveals patterns, archetypes, and outliers. Sometimes this will confirm what the organization suspects, but sometimes it will be completely new knowledge, leading the organization to a new approach. When the data has revealed its insights, the role of the data scientist becomes that of a storyteller, communicating the results to the project stakeholders. Data scientists can use powerful data visualization tools to help the stakeholders understand the nature of the results and the recommended action to take. Data science is changing the way we work. It's changing the way we use data and is changing our approach to the world.
Data science didn't really exist when I was growing up. It's not something that I ever woke up and said, I want to be a data scientist when I grow up. No, it didn't exist. I didn't know I would be working in data science.
When I grew up, there isn't that field called data science, and I think it's really new.
Data science didn't exist until 2009, 2011. Someone like DJ Patil or Andrew Gilman coined the term. Before that, there was statistics, and I didn't want to be any of those. I wanted to be in business, and then I found data science a heck of a lot more interesting.
I studied statistics. That's how I started. I went through many different stages in my life where I wanted to be a singer and then a doctor. And then I realized that I was good at math. So I chose an area that was focused in quantitative analysis. And from then I do think that I wanted to work with data, not necessarily data science as is known today.
The first time that I had contact with data science when I was my first year as a mechanical engineering, and strategic consulting firms, they use data science to make decisions. So it was my first contact with data science.
I had a complicated problem that I needed to solve, and the usual techniques that we had at the time couldn't help with that problem.
I graduated with a math degree in the worst possible time, right after the economic crisis, and you actually had to be useful to get a job. So I went and got a degree in statistics, and then I worked enough jobs that were called data scientists that I suddenly became one.
My undergraduate degree was in business, and I majored in politics, philosophy, and economics. And then I did a master's in business analytics at New York University at the Stern School of Business. When I left my undergrad, the first company I joined, it turned out that they were analyzing electronic point of sale data for retail manufacturers. And what we were doing was data science, but we only really started using that term much later. In fact, I'd say 4 or 5 years ago is when we started calling it analytics and data science.
I had several options for my internship here in Canada, and one of the options was to work with data science. I used to work with product development, but I think that was a good choice. And then I started my internship with data science.
I'm a civil engineer by training, so all engineers work with data. I would say the conventional use of data science in my life started with transportation research. I started building large models, trying to forecast traffic on streets, trying to determine congestion and greenhouse gas emissions or tailpipe emissions. So I think that's where my start was, and I started building these models when I was a graduate student at the University of Toronto, started working with very large data sets, looking at household samples of say 150,000 households, 500,000 trips, and that too I'm speaking from mid-90s, when this was supposed to be a very large data set, but not in today's terms. But that's how I started. I continued working with it, and then I moved to McGill University, where I was a professor of transportation engineering, and I built even bigger data models that involve data and analytics. And so I would say, yes, transportation research brought me to data science. My advice to an aspiring data scientist is to be curious, extremely argumentative, judgmental. Curiosity is absolute must. If you're not curious, you would not know what to do with the data. Judgmental, because if you do not have preconceived notions about things, you wouldn't know where to begin with. Argumentative, because if you can argument and if you can plead a case, at least you can start somewhere, and then you learn from data, and then you modify your assumptions and hypotheses, and your data would help you learn. And you may start at the wrong point. You may say that I thought I believed this, but now with data I know this. So this allows you a learning process. So curiosity, being able to take a position, a strong position, and then moving forward with it. The other thing that a data scientist would need is some comfort and flexibility with analytics platforms, some software, some computing platform, but that's secondary. The most important thing is curiosity and the ability to take positions. Once you've done that, once you've analyzed, then you've got some answers. And that's the last thing that a data scientist needs, and that is the ability to tell a story. That once you have your analytics, once you have your tabulations, now you should be able to tell a great story from it. Because if you don't tell a great story from it, your findings will remain hidden, remain buried, nobody would know. Your rise to prominence is pretty much relying on your ability to tell great stories. A starting point would be to see what is your competitive advantage. Do you want to be a data scientist in any field or a specific field? Because let's say you want to be a data scientist and work for an IT firm or a web-based or internet-based firm, then you need a different set of skills. And if you want to be a data scientist for, let's say, in the health industry, then you need different sets of skills. So figure out first what your interest is and what is your competitive advantage. Your competitive advantage is not necessarily going to be your analytical skills. Your competitive advantage is your understanding of some aspect of life where you exceed beyond others in understanding that. Maybe it's film, maybe it's retail, maybe it's health, maybe it's computers. Once you've figured out where your expertise lies, then you start acquiring analytical skills, what platforms to learn, and those platforms, those tools would be specific to the industry that you're interested in. And then once you have got some proficiency in the tools, the next thing would be to apply your skills to real problems and then tell the rest of the world what you can do with it.
Welcome to Defining Data Science Lesson Summary. In this video, we'll review important points you learned from the videos and readings in this lesson. We'll also link together the ideas from the resources in this lesson. We will quickly recap what data science is, data scientists' role in an organization, what makes a skilled data scientist, and expert advice on how to acquire these skills. Let's begin. So, what really is data science? Simply put, data science is the study of data. Data science uses data to understand the world around us. Some consider data science an art of uncovering the insights and trends hiding behind data. Data analysis isn't new. Recent data access and enhanced computing power drives new insights and knowledge through analysis. We also have the computing power needed to analyze this data to reveal new knowledge. With the power of computers, we can dig through this information to reveal valuable insights, just like a detective uncovering secrets. Data scientists translate the data into stories to generate insights. These insights aid strategic decision-making for companies or institutions. Similar to biological or physical sciences, data science deals with structured and unstructured data. The process of gleaning insights from data includes clarifying the problem, data collection, analysis, pattern recognition, storytelling, and visualization. According to Professor Murtaza Haider from the Ted Rogers School of Management, curiosity, argumentation, and judgment are vital for data scientists. Curiosity helps you explore data and come up with meaningful questions. Good, sound, reasonable arguments help you explain your findings after learning from the data, compelling the listener to adjust their ideas based on the new information. Good judgment guides you to start in the right direction. Skilled data scientists go beyond just being statisticians or computer experts. Companies are looking for versatile individuals who know a lot about a particular subject, have some experience in programming and analyzing data, and can communicate well. Generally, data scientists are comfortable with math. They're curious. They're good at telling stories. Their backgrounds can come from various fields like economics, engineering, medicine, and more. Once you understand your strengths and interests, focus on mastering data analysis in that field and select suitable tools for your industry. As you become proficient, apply your expertise to solve real-world issues using data similar to solving mysteries by deciphering clues. So, what does the future look like for you as a skilled data scientist? Data scientist jobs will also change as technology changes and data roles develop. To ensure their employees are qualified, companies will require certification. Data scientists will always need to think logically, use algorithms, and follow a methodical approach. Most importantly, they must gather data correctly and carefully analyze the models being used, all aiming to achieve successful business results.
I've built a recommendation engine before as part of a large organization and worked through all types of engineers and accounted for different parts of the problem. It's one of the ones I'm most happy with because ultimately I came up with a very simple solution that was easy to understand from all levels, from the executives to the engineers and developers. Ultimately, it was just as efficient as something really complex that I could have spent a lot more time on.
Back in university, we have a problem that we wanted to predict algae blooms. These algae blooms could cause a rise in toxicity of the water, and it could cause problems to the water treatment company. We couldn't predict with our chemical engineering background, so we use artificial neural networks to predict when these blooms will occur, so the water treatment companies could better handle this problem.
In Toronto, the public transit is operated by Toronto Transit Commission. We call them TTC. It's one of the largest transit authorities in the region in North America. And one day they contacted me and said, we have a problem. And I said, okay, what's the problem? I said, well, we have complaints data and we would like to analyze it and we need your help. I said, fine, I'll be very happy to help. So I said, how many complaints do you have? They said, a few. I said, how many? Maybe 500,000. I said, well, let's start working with it. So I got the data and I started analyzing it. So basically they have done a great job of keeping the data, some data in tabular format, other was unstructured data. And in that case, tabular data was when the complaint arrived, who received it, what was the type of the complaint, was it resolved, whose fault was it. And the unstructured part of it was the exchange of emails and faxes. So imagine looking at 500,000 exchanges of emails and trying to get some answer from it. So I started working with it, and the first thing I wanted to know is why would people complain, and is there a pattern? Are there some days where there are more complaints than others? And I looked at the data and I analyzed it in all different formats, and I couldn't find what the impetus for complaints being higher on a certain day and lower on others. And it continued for maybe a month or so, and then one day I was getting off the bus in Toronto. And I was still thinking about it, and I stepped out without looking at on the ground, and I stepped into a puddle of water, and now I was sort of ankle deep into water, and it was just 1 foot wet and the other dry, and I was extremely annoyed. And I was walking back, and then it hit me, and I said, well, wait a second. Today it rained unexpectedly, and I wasn't prepared for it. That's why I'm wet, and I wasn't looking for it. What if there is a relationship between extreme weather and the type of complaints TTC receives? So I went to the Environment Canada's website and I got data on rain and precipitation, wind and the like. And there I found something very interesting. The 10 most excessive days for complaints, the 10 days where people complained the most, were the days when the weather was bad. It was unexpected rain, an extreme drop in temperature, too much snow, very windy day. So I went back to the TTC's executives and I said, I've got good news and bad news. And so good news is I know why people would complain excessively on certain days. I know the reason for it. The bad news is there's nothing you can do about it.
I'm Norman White. I'm a clinical faculty member in the IOMS department, Information Operations and Management Science department here at Stern. I've been here for a long time, since I got out of college pretty much. I'm sort of a techie, geeky kind of person. I really like to play with technology in my spare time. I'm currently faculty director of the Stern Center for Research Computing, in which we have a private cloud that runs lots of different kinds of systems. Many of our faculty or PhD students who need specialized hardware and software will come to us. We'll spin up a machine for them, configure it, help them and advise on them. And a lot of the data scientists, or virtually all the data scientists at Stern, use our facilities. And their PhD students use them a lot. I have an undergraduate degree in applied physics, and while I was an undergrad, I took a number of economics courses, so I ended up deciding to go to business school. But I had, this was in the early days of computers, and I had gotten interested in computers. And I came to Stern, which was then NYU Business School downtown, and they had a little computer center. And I decided that I was going to learn two things while I was there. One, I was going to learn how to program. I'd taken one programming course in college. And I was going to learn how to touch type. I never did learn how to touch type. Oh, I did, maybe I did, but I forgot. Now I'm back to two-finger pecking. But I became a self-taught programmer, and then I took a number of courses at IBM because I eventually became the director of the computer center while I was getting my PhD in economics and statistics at Stern. So in 1973, the school formed a department called Computer Applications and Information Systems, and I was one of the first faculty members in the department, and I've been here ever since. So my typical Monday is I usually get in around 11 o'clock, and I do my email at home first, but I come in and I have two classes on Monday. I have a class on design and development of web-based systems at 6 o'clock. 2 o'clock I have a dealing with data class. The class is based all on Python notebooks. So we start with sort of the basics of Unix and Linux, just to get the students used to that. We move on to some Python, some regular expressions, a lot of relational databases, some Python pandas, which is sort of like R for Python, lets you do mathematical and statistical calculations in Python. And then I end up with big data, for which, as you probably know, I'm an evangelist. And the students have weekly homeworks. I put them in teams, and they have to do a big project at the end of the term, and they do some really cool things. Yes, in fact, the whole course is taught using Jupyter Notebooks. Every student has their own virtual machine on Amazon Web Services. So we pre-configure all the machines, and they get a standard image that has all of the materials for the course, either loaded on it or in a Jupyter Notebook, there are the commands to download it or update the server with the right software. So everybody's in the same environment. It doesn't matter whether they have a Mac or a Windows machine or how old it is. Everybody can do everything in the class.
As a data professional, you will be working with a variety of data file types and formats. It is important to understand the underlying structure of file formats along with their benefits and limitations. This understanding will support you to make the right decisions on the formats best suited for your data and performance needs. Some of the standard file formats that we will cover in this video include delimited text file formats, Microsoft Excel Open XML Spreadsheet, or XLSX, Extensible Markup Language, or XML, Portable Document Format, or PDF, JavaScript Object Notation, or JSON. Delimited text files are text files used to store data as text in which each line or row has values separated by a delimiter, where a delimiter is a sequence of one or more characters for specifying the boundary between independent entities or values. Any character can be used to separate the values, but most common delimiters are the comma, tab, colon, vertical bar, and space. Comma-separated values, or CSVs, and tab-separated values, or TSVs, are the most commonly used file types in this category. In CSVs, the delimiter is a comma, while in TSVs, the delimiter is a tab. When literal commas are present in text data and therefore cannot be used as delimiters, TSVs serve as an alternative to CSV format. Tab stops are infrequent in running text. Each row or horizontal line in the text file has a set of values separated by the delimiter and represents a record. The first row works as a column header, where each column can have a different type of data. For example, a column can be of date type, while another can be a string or integer type data. Delimited files allow field values of any length and are considered a standard format for providing straightforward information schema. They can be processed by almost all existing applications. Delimiters also represent one of various means to specify boundaries in a data stream. Microsoft Excel Open XML Spreadsheet, or XLSX, is a Microsoft Excel Open XML file format that falls under the spreadsheet file format. It is an XML-based file format created by Microsoft. In an XLSX, also known as a workbook, there can be multiple worksheets, and each worksheet is organized into rows and columns, at the intersection of which is the cell. Each cell contains data. XLSX uses the open file format, which means it is generally accessible to most other applications. It can use and save all functions available in Excel and is also known to be one of the more secure file formats as it cannot save malicious code. Extensible Markup Language, or XML, is a markup language with set rules for encoding data. The XML file format is both readable by humans and machines. It is a self-descriptive language designed for sending information over the internet. XML is similar to HTML in some respects, but also has differences. For example, an XML does not use predefined tags like HTML does. XML is platform independent and programming language independent, and therefore simplifies data sharing between various systems. Portable Document Format, or PDF, is a file format developed by Adobe to present documents independent of application software, hardware, and operating systems, which means it can be viewed the same way on any device. This format is frequently used in legal and financial documents and can also be used to fill in data such as forms. JavaScript Object Notation, or JSON, is a text-based open standard designed for transmitting structured data over the web. The file format is a language-independent data format that can be read in any programming language. JSON is easy to use, is compatible with a wide range of browsers, and is considered as one of the best tools for sharing data of any size and type, even audio and video. That is one reason many APIs and web servers return data as JSON.
I really enjoy regression. I'd say regression was maybe one of the first concepts that really helped me understand data, so I enjoy regression.
I really like data visualization. I think it's a key element for people to get across their message to people that don't understand that well what data science is.
Artificial neural networks.
I'm really passionate about neural networks because we have a lot to learn with nature. So when we are trying to mimic our brain, I think that we can do some applications with this behavior, this biological behavior in algorithms.
Data visualization with R, I love to do this.
Nearest neighbor. It's the simplest, but it just gets the best results so many more times than some overblown, overworked algorithm that's just as likely to overfit as it is to make a good fit.
So structured data is more like tabular data, things that you're familiar with in Microsoft Excel format. You've got rows and columns, and that's called structured data. Unstructured data is basically data that is coming from mostly from web, where it's not tabular. It's not in rows and columns. It's text. It's sometimes it's video and audio. So you would have to deploy more sophisticated algorithms to extract data. And in fact, a lot of times we take unstructured data and spend a great deal of time and effort to get some structure out of it and then analyze it. So if you have something which fits nicely into tables and columns and rows, go ahead, that's your structured data. But if you see if it's a weblog, or if you're trying to get information out of web pages and you've got a gazillion web pages, that's unstructured data. That would require a little bit more effort to get the information out of it. There are thousands of books written on regression and millions of lectures delivered on regression, and I always feel that they don't do a good job of explaining regression because they get into data and models and statistical distributions. Let's forget about it. Let me explain regression in the simplest possible terms. If you have ever taken a cab ride, a taxi ride, you understand regression. Here's how it works. The moment you sit in a cab, you see that there's a fixed amount there. It says $2.50. Whether the cab moves or you get off, this is what you owe to the driver. The moment you step into a cab, that's a constant. You have to pay that amount if you have stepped into a cab. Then as it starts moving, for every meter or 100 meters, the fare increases by a certain amount. So there's a fraction, there's a relationship between distance and the amount you would pay above and beyond that constant. And if you're not moving and you're stuck in traffic, then every additional minute you have to pay more. So as the minutes increase, your fare increases. As the distance increases, your fare increases. And while all this is happening, you've already paid a base fare, which is the constant. This is what regression is. Regression tells you what the base fare is and what is the relationship between time and the fare you have paid and the distance you've traveled and the fare you've paid. Because in the absence of knowing those relationships and just knowing how much people traveled for and how much they paid, regression allows you to compute that constant that you didn't know it was 250, and it would compute the relationship between the fare and the distance and the fare and the time. That's a regression.
Welcome to a realm where data isn't just numbers. It's the gateway to innovation, discovery, and the endless possibilities that lie ahead. To understand the heart and soul of a data scientist world, let's review what data scientists do, as discussed in the readings and videos from this lesson. Data scientists investigate and find explanations for many problems. For example, Dr. Mortaza Haider found an explanation for why 500,000 customers complained about public transit in Toronto. After much investigation, he found a relationship between unexpected bad weather events and the number of complaints on that particular day. Data scientists may tackle environmental challenges, such as predicting algae blooms to prevent water toxicity. By harnessing data and the prowess of artificial neural networks, data scientists can help water treatment companies safeguard the ecosystem. Norman White, a clinical faculty member at the Stern School of Business, also discussed the journey that led him to build a recommendation engine that simplified intricate problems across departments. This underscores the essence of data science, solving real-world issues with innovative solutions. Education serves as a cornerstone, equipping future data scientists with essential skills. Dr. White's classroom comes alive with Python notebooks, revealing the secrets of Unix, Linux, relational databases, and powerful tools like pandas. Dr. Vincent Granville, an author on data science, lists algebra, calculus, and training in probability and statistics as necessary educational backgrounds to be a data scientist. He distinguishes between a statistician and a data scientist. A data scientist uses statistics, but is not only a statistician. However, data scientists do use a lot of statistical models, such as statistical regression. Regression shows the probable relationship between two variables, such as the distance you drive and the amount of gas you use. Data scientists also utilize machine learning algorithms such as nearest neighbor to process what much of the media refers to as big data. The term should be used with caution. What was once considered big data is continually reshaped by innovation. Tools like Hadoop and software advancements have shattered traditional limits, ushering in a new era of possibilities. Neither does Dr. Patil restrict data scientists to dealing with data sets of arbitrary size, nor does he restrict them to using particular tools. His definition includes individuals of various academic backgrounds and training. A data scientist not only unlocks the insights within a data set, but conveys a compelling narrative to stakeholders. It's this blend of technical acumen and communication finesse that sets them apart. The data that data scientists use comes from a wide variety of sources, sometimes video, sometimes audio, and often unformatted text. Text-based data can also be structured, such as in tables with rows and columns, or unstructured, like emails or logs. The data they work with comes in a wide variety of formats, such as delimited text files, spreadsheets, XML, PDFs, and JavaScript object notation, or JSON. What makes a data scientist truly exceptional? The answer, according to Rachel Schutt, chief data scientist at News Corp, lies in curiosity. A successful data scientist is a blend of computer scientist, software engineer, and statistician. Their ability to transform unstructured solutions into structured insights defines their prowess. As we reflect on the insights from A Day in the Life of a Data Scientist, we realize that data science isn't just a profession. It's a journey of exploration, innovation, and storytelling. The world of data is vast, and the data scientist, armed with skills, curiosity, and determination, navigates it to unravel the extraordinary.
Digital transformation affects business operations, updating existing processes and operations and creating new ones to harness the benefits of new technologies. This digital change integrates digital technology into all areas of an organization, resulting in fundamental changes to how it operates and delivers value to customers. It is an organizational and cultural change driven by data science and especially big data. The availability of vast amounts of data and the competitive advantage that analyzing it brings has triggered digital transformations throughout many industries. Netflix moved from being a postal DVD lending system to one of the world's foremost video streaming providers. The Houston Rockets NBA team used data gathered by overhead cameras to analyze the most productive plays, and Lufthansa analyzed customer data to improve its service. Organizations all around us are changing to their very core. Let's take a look at an example to see how big data can trigger a digital transformation, not just in one organization, but in an entire industry. In 2018, the Houston Rockets, a National Basketball Association, or NBA team, raised their game using big data. The Rockets were one of 4 NBA teams to install a video tracking system which mined raw data from games. They analyzed video tracking data to investigate which plays provided the best opportunities for high scores, and discovered something surprising. Data analysis revealed that the shots that provide the best opportunities for high scores are 2-point dunks from inside the 2-point zone and 3-point shots from outside the 3-point line, not long-range 2-point shots from inside it. This discovery entirely changed the way the team approached each game, increasing the number of 3-point shots attempted. In the 2017-18 season, the Rockets made more 3-point shots than any other team in NBA history, and this was a major reason they won more games than any of their rivals. In basketball, big data changed the way teams try to win, transforming the approach to the game. Digital transformation is not simply duplicating existing processes in digital form. The in-depth analysis of how the business operates helps organizations discover how to improve their processes and operations, and harness the benefits of integrating data science into their workflows. Most organizations realize that digital transformation will require fundamental changes to their approach towards data, employees, and customers, and it will affect their organizational culture. Digital transformation impacts every aspect of the organization, so it is handled by decision makers at the very top levels to ensure success. The support of the Chief Executive Officer is crucial to the digital transformation process, as is the support of the Chief Information Officer. and the emerging role of Chief Data Officer. But they also require support from the executives who control budgets, personnel decisions, and day-to-day priorities. This is a whole organization process. Everyone must support it for it to succeed. There is no doubt dealing with all the issues that arise in this effort requires a new mindset, but digital transformation is the way to succeed now and in the future.
Welcome to Introduction to Cloud Computing and Cloud Deployment and Service Models. After watching this video, you will be able to describe cloud computing concepts, define cloud deployment models and cloud service models, and identify the characteristics of cloud computing. Cloud computing, also referred to as the cloud, is the delivery of on-demand computing resources such as networks, servers, storage, applications, services, and data centers over the internet on a pay-for-use basis. The term cloud computing can be used to describe applications and data that users access over the internet rather than on their local computer. Examples of cloud computing include users using online web apps, employees using secure online business applications to conduct their work, and users storing personal files on cloud-based storage platforms such as Google Drive, OneDrive, and Dropbox. One of the main user benefits of cloud computing is that instead of users needing to purchase their own applications and install them locally on their computer, they can use online versions of those applications and pay a monthly subscription. Not only is this typically more cost-effective initially, but users can also access the latest version of the application without having to purchase a full retail copy of the newer version. A side advantage of this is that the user also saves lots of local storage space as the application is hosted online. And the beauty of most cloud-based applications is that they also enable users to work collaboratively with their colleagues working on the same files in real time and being able to see each other's edits and updates. Cloud computing is composed of 5 essential characteristics, 3 deployment models, and 3 service models. Let's start with understanding the 5 essential characteristics of the cloud. On-demand self-service means that you get access to cloud resources such as the processing power, storage, and network you need using a simple interface without requiring human interaction with each service provider. Broad network access means that cloud computing resources can be accessed via the network through standard mechanisms and platforms such as mobile phones, tablets, laptops, and workstations. Resource pooling is what gives cloud providers economies of scale, which they pass on to their customers, making cloud cost-efficient. Using a multi-tenant model, computing resources are pooled to serve multiple consumers, and cloud resources are dynamically assigned and reassigned according to demand, without customers needing to know the physical location of these resources. Rapid elasticity implies that you can access more resources when you need them and scale back when you don't, because resources are elastically provisioned and released. And measured service means that you only pay for what you use or reserve as you go. If you're not using resources, you're not paying. Resource usage is monitored, measured, and reported transparently based on consumer utilization. As you have seen, cloud computing is really about using technology as a service, leveraging remote systems on demand over the open internet, scaling up and scaling back, and paying for what you use. And it has changed the way the world consumes compute services by making them more cost-efficient while also making organizations more agile in response to changes in their markets. Cloud deployment models indicate where the infrastructure resides, who owns and manages it, and how cloud resources and services are made available to users. There are 3 types of cloud deployment models: public, private, and hybrid. Public cloud is when you leverage cloud services over the open internet on hardware owned by the cloud provider, but its usage is shared by other companies. Private cloud means that the cloud infrastructure is provisioned for exclusive use by a single organization. It could run on premises, or it could be owned, managed, and operated by a service provider. And when you use a mix of both public and private clouds working together seamlessly, that is classified as the hybrid cloud model. Now, let's look at the three cloud service models that are based on the three layers in a computing stack: infrastructure, platform, and application. These cloud computing models are aptly referred to as infrastructure as a service, or IaaS, platform as a service, or PaaS, and software as a service, or SaaS. In an IaaS model, you can access the infrastructure and physical computing resources, such as servers, networking, storage, and data center space, without the need to manage or operate them. In a PaaS model, you can access the platform that comprises the hardware and software tools that are usually needed to develop and deploy applications to users over the internet. And an SaaS is a software licensing and delivery model in which software and applications are centrally hosted and licensed on a subscription basis. It is sometimes referred to as on-demand software. In this video, you learned that cloud computing is the delivery of on-demand computing resources over the internet on a pay-for-use basis. Cloud computing is composed of 5 essential characteristics, 3 deployment models, and 3 service models. The 5 essential characteristics of cloud computing are on-demand self-service, broad network access, resource pooling, rapid elasticity, and measured service. There are 3 types of cloud deployment models: public, private, and hybrid. And the 3 cloud service models are based on the 3 layers in a computing stack: infrastructure, platform, and application, and they are referred to as infrastructure as a service, or IaaS, platform as a service, or PaaS, and software as a service, or SaaS.
Cloud it's a godsend for data scientists, primarily because you're able to take you take your data, take your information, and put it in the cloud, put it in a central storage system. It allows you to bypass the physical limitations of the computers and the systems you're using, and it allows you to deploy the analytics and storage capacities of advanced machines that do not necessarily have to be your machine or your company's machine. Cloud allows you not just to store large amounts of data on servers somewhere in California or in Nevada, but it also allows you to deploy very advanced computing algorithms and the ability to do high performance computing using machines that are not yours. So think of it as you have some information, you can't store it, so you send it to storage space, let's call it cloud, and the algorithms that you need to use, you don't have them with you, but then on the cloud you have those algorithms available. So what you do is you deploy those algorithms on very large data sets, and you're able to do it even though your own systems, your own machines, your own computing environments were not allowing you to do so. So cloud is beautiful. And the other thing cloud is beautiful for is that it allows multiple entities to work with same data at the same time. So you can be working with the same data that your colleagues in, say, Germany, and another team in India, and another team in Ghana, they are collectively working, and they are able to do so because the information and the algorithms and the tools and the answers and the results, whatever they needed, is available at a central place, which we call cloud. So cloud is beautiful.
Using the cloud enables you to get instant access to open source technologies like Apache Spark without the need to install and configure them locally. Using the cloud also gives you access to the most up-to-date tools and libraries without the worry of maintaining them and ensuring that they are up to date. The cloud is accessible from everywhere and in every time zone. You can use cloud-based technologies from your laptop, from your tablet, and even from your phone, enabling collaboration more easily than ever before. Multiple collaborators or teams can access the data simultaneously, working together on producing a solution. Some big tech companies offer cloud platforms, allowing you to become familiar with cloud based technologies in a pre built environment. IBM offers the IBM Cloud, Amazon offers Amazon Web Services or AWS, and Google offers Google Cloud Platform. IBM also provides Skills Network Labs, or SN Labs, to learners register to any of the learning portals on the IBM Developer Skills Network, where you have access to tools like Jupyter Notebooks and Spark clusters, so you can create your own data science project and develop solutions. With practice and familiarity, you will discover how the cloud dramatically enhances productivity for data scientists. In this digital world, everyone leaves a trace. From our travel habits to our workouts and entertainment, the increasing number of internet-connected devices that we interact with on a daily basis record vast amounts of data about us. There's even a name for it: big data. Ernst & Young offers the following definition. Big data refers to the dynamic, large, and disparate volumes of data being created by people, tools, and machines. It requires new, innovative, and scalable technology to collect, host, and analytically process the vast amount of data gathered in order to derive real-time business insights that relate to consumers, risk, profit, performance, productivity management, and enhanced shareholder value. There is no one definition of big data, but there are certain elements that are common across the different definitions, such as velocity, volume, variety, veracity, and value. These are the V's of big data. Velocity is the speed at which data accumulates. Data is being generated extremely fast in a process that never stops. Near or real-time streaming, local, and cloud-based technologies can process information very quickly. Volume is the scale of the data, or the increase in the amount of data stored. Drivers of volume are the increase in data sources, higher resolution sensors, and scalable infrastructure. Variety is the diversity of the data. Structured data fits neatly into rows and columns in relational databases, while unstructured data is not organized in a predefined way, like tweets, blog posts, pictures, numbers, and video. Variety also reflects that data comes from different sources: machines, people, and processes, both internal and external to organizations. Drivers are mobile technologies, social media, wearable technologies, geotechnologies, video, and many, many more. Veracity is the quality and origin of data and its conformity to facts and accuracy. Attributes include consistency, completeness, integrity, and ambiguity. Drivers include cost and the need for traceability. With the large amount of data available, the debate rages on about the accuracy of data in the digital age. Is the information real or is it false? Value is our ability and need to turn data into value. Value isn't just profit. It may have medical or social benefits, as well as customer, employee, or personal satisfaction. The main reason that people invest time to understand big data is to derive value from it. Let's look at some examples of the V's in action. Velocity. Every 60 seconds, hours of footage are uploaded to YouTube, which is generating data. Think about how quickly data accumulates over hours, days, and years. Volume. The world population is approximately 7 billion people, and the vast majority are now using digital devices: mobile phones, desktop and laptop computers, wearable devices, and so on. These devices all generate, capture, and store data, approximately 2.5 quintillion bytes every day. That's the equivalent of 10 million Blu-ray DVDs. Variety. Let's think about the different types of data: text, pictures, film, sound, health data from wearable devices, and many different types of data from devices connected to the Internet of Things. Veracity. 80% of data is considered to be unstructured, and we must devise ways to produce reliable and accurate insights. The data must be categorized, analyzed, and visualized. Data scientists today derive insights from big data and cope with the challenges that these massive data sets present. The scale of the data being collected means that it's not feasible to use conventional data analysis tools. However, alternative tools that leverage distributed computing power can overcome this problem. Tools such as Apache Spark, Hadoop, and its ecosystem provides ways to extract, load, analyze, and process the data across distributed compute resources, providing new insights and knowledge. This gives organizations more ways to connect with their customers and enrich the services they offer. So next time you strap on your smartwatch, unlock your smartphone, or track your workout, remember your data is starting a journey that might take it all the way around the world through big data analysis and back to you.
Everybody knows how to program at least a little bit. They all have a little bit of programming background at least. And some of them have a lot. Some of them are Masters of Science in Computer Science. Some of them are MBA students who've come in from technical fields and programmed every day. And others are ones who maybe took a programming course in college 4 or 5 years ago, but at least they can think computationally. And that which I think is the most important thing that they need. Data science and business analytics have become very hot subjects in the last 4 or 5 years. We have new tools, we have new approaches, and we have lots and lots of data that traditional techniques just couldn't really store and handle. And I think the word is out. I think at this point, at first, companies and employers understood the need, especially in certain fields. I can remember talking to a major bank 3 years ago about big data, and there was one little group in the bank where one person had a little effort and put a little cluster together. Now that same bank has 5 or 6 major big data clusters, and they're putting all of their credit card data in it, and they're grinding it upside down and sideways, using all sorts of data science kinds of techniques. 2 years ago, or was it last year, I think, our undergraduate dealing with data course had 28 students in it. This year, it has 140. So that means that the parents are now beginning to get the word. Because one thing we understand with our undergrads is the parents who are paying very hefty tuitions, they tell their sons and daughters, you should be an accountant, right? Or you should go into financial services or into marketing, because this is where the money is. Now they're getting the word that maybe you should take some more sort of STEM classes in high school and be ready to go into data science or go into fields where analytics is just playing more and more, has become more and more important. It depends on who you are. I have my own definition of big data. My definition of big data is data that is large enough and has enough volume and velocity that you cannot handle it with traditional database systems. Some of our statisticians think big data is something you can't fit on a thumb drive. Big data, to me, was started by Google. When Google tried to figure out how they were, when Larry Page and Sergey Brin wanted to basically figure out how to solve their PageRank algorithm, there was nothing out there. They were trying to store all of the web pages in the world, and there was no technology, there was no way to do this, and so they went out and developed this approach, which is now it's now Hadoop has copied it, but this is where all these large big data clusters are found. But big data has now also expanded into how do you analyze. There are new analytical techniques and statistical techniques for handling these really, really, really large data sets. We'll probably get to deep learning at some point along here, but. Traditionally, in computation and processing data, we would bring the data to the computer. You'd run a program and you'd bring the data into the program. In a big data cluster, what Larry Page and Sergey Brin came up with, this pretty simple, is they took the data and they sliced it into pieces. And they distributed each, and they replicated each piece or triplicated each piece. And they would send it, the pieces of these files, to thousands of computers. First it was hundreds, but then now it's thousands, now it's tens of thousands. And then they would send the same program to all these computers in the cluster. And each computer would run the program on its little piece of the file and send the results back. The results would then be sorted, and those results would then be redistributed back to another process. The first process is called a map or a mapper process, and the second one was called a reduce process. Fairly simple concepts, but it turned out that you could do lots and lots of different kinds of, handle lots and lots of different kinds of problems in very, very, very large data sets. So the one thing that's nice about these big data clusters is they scale linearly. You add twice as many servers and you get twice the performance and you can handle twice the amount of data. So this just broke a bottleneck for all the major social media companies. Yahoo then got on board. Yahoo hired someone named Doug Cutting, who had been working on a clone or a copy of the Google Big Data architecture, and that's now called Hadoop. And if you Google Hadoop, you'll see that it's a now very popular term. And there are many, 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 if you look at the big data ecology, there are hundreds, if not thousands of companies out there that have some kind of footprint in the big data world. Most of the components of data science have been around for many, 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 many decades, but they're all coming together now with some new nuances, I guess. At the bottom of data science, you see probability and statistics. You see algebra, linear algebra. You see programming, and you see databases. They've all been here. But what's happened now is we now have the computational capabilities to apply some new techniques, machine learning, where now we can take really large data sets, and instead of taking a sample and trying to test some hypothesis, we can take really, really large data sets and look for patterns. And so back off one level from hypothesis testing to finding patterns that maybe will generate hypotheses. Now this can bother some very traditional statisticians and gets them really annoyed sometimes that you're supposed to have a hypothesis that is independent of the data, and then you test it. So once some of these machine learning techniques were really the only way you could analyze some of these really large social media data sets. So what we've seen is that the combination of traditional areas, computer science, probability, statistics, mathematics, all coming together in this thing that we call decision sciences. Our department at Stern, I'll give a little plug here, we happen to have been very well situated among business schools because we're one of the few business schools that has a real statistics department with real PhD level statisticians in it. We have an operations management department, and an information systems department. So we have a wide range of computer scientists to statisticians to operations researchers. And so we were like perfectly positioned, as a couple of other business schools were, to jump onto this bandwagon and say, okay, this is decision sciences. And Foster Provo, who's in my department, was the first director of the NYU Center for Data Science. 4 years ago, maybe 5 years ago. I mean, this is one of those cases where you can just go to Google and search for data science and see how often it occurred, and you'll see almost nothing, and then just a spike. The same thing you would see with big data about 7 or 8 years ago. So data science is a term I hadn't heard of probably 5 years ago. The first question is, what is it? And I think faculty and everybody's still trying to get their hands around exactly what is business analytics and what is data science. We certainly know the components of it, but it's morphing and changing and growing. I mean, in the last 3 years, deep learning has just been added into the mix. Neural networks have been around for 20 or 30 years. 20 years ago, I would teach neural networks in a class, and you really couldn't do very much with them. And now, some researchers have come up with multi-layer neural networks in Toronto, in particular, at the University of Toronto. And that technology is now rapidly expanding. It's being used by Google, by Facebook, by lots of companies.
The big data processing technologies provide ways to work with large sets of structured, semi-structured, and unstructured data so that the value can be derived from big data. In some of the other videos, we discussed big data technologies such as NoSQL databases and data lakes. In this video, we are going to talk about 3 open source technologies and the role they play in big data analytics: Apache Hadoop, Apache Hive, and Apache Spark. Hadoop is a collection of tools that provides distributed storage and processing of big data. Hive is a data warehouse for data query and analysis built on top of Hadoop. Spark is a distributed data analytics framework designed to perform complex data analytics in real time. Hadoop, a Java-based open source framework, allows distributed storage and processing of large datasets across clusters of computers. In Hadoop distributed system, a node is a single computer, and a collection of nodes forms a cluster. Hadoop can scale up from a single node to any number of nodes, each offering local storage and computation. Hadoop provides a reliable, scalable, and cost-effective solution for storing data with no format requirements. Using Hadoop, you can incorporate emerging data formats such as streaming audio, video, social media sentiment, and clickstream data along with structured, semi-structured, and unstructured data not traditionally used in a data warehouse. Provide real-time, self-service access for all stakeholders. Optimize and streamline costs in your enterprise data warehouse by consolidating data across the organization and moving cold data, that is, data that is not in frequent use, to a Hadoop-based system. One of the 4 main components of Hadoop is Hadoop Distributed File System, or HDFS, which is a storage system for big data that runs on multiple commodity hardware connected through a network. HDFS provides scalable and reliable big data storage by partitioning files over multiple nodes. It splits large files across multiple computers, allowing parallel access to them. Computations can, therefore, run in parallel on each node where data is stored. It also replicates file blocks on different nodes to prevent data loss, making it fault-tolerant. Let's understand this through an example. Consider a file that includes phone numbers for everyone in the United States. The numbers for people with last names starting with an A might be stored on server 1, B on server 2, and so on. With Hadoop, pieces of this phone book would be stored across the cluster. To reconstruct the entire phone book, your program would need the blocks from every server in the cluster. HDFS also replicates these smaller pieces into 2 additional servers by default, ensuring availability when a server fails. In addition to higher availability, this offers multiple benefits. It allows the Hadoop cluster to break up work into smaller chunks and run those jobs on all servers in the cluster for better scalability. Finally, you gain the benefit of data locality, which is the process of moving the computation closer to the node on which the data resides. This is critical when working with large datasets because it minimizes network congestion and increases throughput. Some of the other benefits that come from using HDFS include fast recovery from hardware failures, because HDFS is built to detect faults and automatically recover. Access to streaming data, because HDFS supports high data throughput rates. Accommodation of large data sets, because HDFS can scale to hundreds of nodes or computers in a single cluster. Portability, because HDFS is portable across multiple hardware platforms and compatible with a variety of underlying operating systems. Hive is an open-source data warehouse software for reading, writing, and managing large dataset files that are stored directly in either HDFS or other data storage systems such as Apache HBase. Hadoop is intended for long sequential scans, and because Hive is based on Hadoop, queries have very high latency, which means Hive is less appropriate for applications that need very fast response times. Also, Hive is read-based and therefore not suitable for transaction processing that typically involves a high percentage of write operations. Hive is better suited for data warehousing tasks such as ETL, reporting, and data analysis, and includes tools that enable easy access to data via SQL. This brings us to Spark, a general-purpose data processing engine designed to extract and process large volumes of data for a wide range of applications, including interactive analytics, streams processing, machine learning, data integration, and ETL. It takes advantage of in-memory processing to significantly increase the speed of computations and spilling to disk only when memory is constrained. Spark has interfaces for major programming languages, such as Java, Scala, Python, R, and SQL. It can run using its standalone clustering technology, as well as on top of other infrastructures such as Hadoop. And it can access data in a large variety of data sources, including HDFS and Hive, making it highly versatile. The ability to process streaming data fast and perform complex analytics in real time is the key use case for Apache Spark.
Welcome to the Big Data and Data Mining Lesson Summary video. In this lesson, you gained insights into the impact of big data on various aspects of society, from business operations to sports, and developed an understanding of key attributes and challenges associated with big data. In this video, we will recap fundamentals of big data and how big data drives digital transformation, how data scientists leverage the essential characteristics of the cloud to gain insights from big data, the data mining process, and common tools used to process big data. The availability of vast amounts of data, resulting in what we now call big data, is driving transformation in business and industry, and consequently, how we live our daily lives. Organizations realize that we require fundamental changes to their approach to business, impacting every aspect of the organization. The availability of so many disparate amounts of data created by people, tools, and machines requires new, innovative, and scalable technology. Big data drives us to derive real-time business insights relating to consumers, risk, profit, performance productivity management, and ultimately enhancing business values. Not everyone agrees on the definition of big data, but people generally agree on the 5 characteristics of this data: value, volume, velocity, variety, and veracity. People expect investing time in studying big data will create value. Volume refers to the scale of the data. Drivers of volume include increasing collectible data sources and scalable infrastructure. Velocity indicates ever-increasing sources of non-stop processes that generate data quickly. Variety reflects that related data comes from different sources, both structured and unstructured. Veracity refers to the quality and origin of data, and that it accurately conforms to facts. The development of cloud and cloud technologies enables us to work with big data. Cloud refers to the delivery of on-demand computing resources on a pay-for-use basis. Cloud computing has 5 essential characteristics: on-demand, network access, resource pooling, elasticity, and measured service. On-demand means access to processing power, storage, and network that you need. These computing resources can be accessed via a network with internet access. Resource pooling allows providers to service multiple consumers with the resources dynamically assigned according to demand, making cloud computing cost-efficient. Elasticity means that you can access resources as you need them and automatically scale back when you don't. With measured service, you only pay for what you use or reserve as you go. You also gain an understanding of how cloud computing addresses challenges related to scalability, collaboration, accessibility, and software maintenance, making it a valuable resource for data analysis and other computational tasks. The cloud gives you instant access to technologies without needing to install or configure them, and provides updated versions of these tools as they get released. Popular open source tools to compute using big data include Apache Hadoop, Apache Hive, and Apache Spark. Hadoop provides distributed storage and processing tools across clusters of computers. Hive is a data warehouse for data query and analysis built on top of Hadoop. Hive allows you to read, write, and manage large data sets directly in the Hadoop file system, or HDFS, or Apache HBase. Spark provides a general-purpose data processing engine designed to extract and process large volumes of data for a wide range of applications. Big data requires a process called data mining to make use of. This 6-step process includes goal setting, selecting data sources, pre-processing, transforming, mining, and evaluation. In the first step, goal setting, you identify key questions you want to answer. Concerns about cost and benefit should inform this step. Once you identify the questions, select the data by identifying sources or planning data collection initiatives. In the next step, pre-processing, you identify irrelevant attributes of data and erroneous aspects of the data by flagging them as necessary. After pre-processing, you transform the data by determining the appropriate format to store the data. Now you get to mine the data, which includes determining analysis methods and the machine learning algorithms you will use to process the data. Once the data has been mined, you finally must evaluate your outcomes by testing the predictive capabilities of the models on the observed data to find effectiveness and efficiency of your algorithms. In addition, you share your results with stakeholders. This entire process should be conducted iteratively, as your results from this iteration will inform further data mining efforts. In summary, big data characteristics that data scientists agree on, even though they might not agree on the exact definition, include value, volume, velocity, and veracity. Data with these qualities is driving transformation across industries and in our daily lives. In large part, cloud technologies enable us to handle big data because they provide ubiquitous access to computational power and storage capacity. Open source cloud-based tools such as Hadoop, Hive, and Spark leverage these advantages, allowing us to effectively and efficiently mine big data.
In data science, there are many terms that are used interchangeably, so let's explore the most common ones. The term big data refers to data sets that are so massive, so quickly built, and so varied that they defy traditional analysis methods, such as you might perform with a relational database. The concurrent development of enormous compute power in distributed networks and new tools and techniques for data analysis means that organizations now have the power to analyze these vast datasets, and new knowledge and insights are becoming available to everyone. Big data is often described in terms of 5 V's: velocity, volume, variety, veracity, and value. Data mining is the process of automatically searching and analyzing data, discovering previously unrevealed patterns. It involves pre-processing the data to prepare it and transforming it into an appropriate format. Once this is done, insights and patterns are mined and extracted using various tools and techniques ranging from simple data visualization tools to machine learning and statistical models. Machine learning is a subset of AI that uses computer algorithms to analyze data and make intelligent decisions based on what it has learned without being explicitly programmed. Machine learning algorithms are trained with large sets of data, and they learn from examples. They do not follow rules-based algorithms. Machine learning is what enables machines to solve problems on their own and make accurate predictions using the provided data. Deep learning is a specialized subset of machine learning that uses layered neural networks to simulate human decision-making. Deep learning algorithms can label and categorize information and identify patterns. It is what enables AI systems to continuously learn on the job and improve the quality and accuracy of results by determining whether decisions were correct. Artificial neural networks, often referred to simply as neural networks, take inspiration from biological neural networks, although they work quite a bit differently. A neural network in AI is a collection of small computing units called neurons that take incoming data and learn to make decisions over time. Neural networks are often layered deep and are the reason deep learning algorithms become more efficient as the datasets increase in volume, as opposed to other machine learning algorithms that may plateau as data increases. Now that you have a broad understanding of the differences between some key AI concepts, there is one more differentiation that is important to understand: that between artificial intelligence and data science. Data science is the process and method for extracting knowledge and insights from large volumes of disparate data. It's an interdisciplinary field involving mathematics, statistical analysis, data visualization, machine learning, and more. It's what makes it possible for us to appropriate information, see patterns, find meaning from large volumes of data, and use it to make decisions that drive business. Data science can use many of the AI techniques to derive insight from data. For example, it could use machine learning algorithms and even deep learning models to extract meaning and draw inferences from data. There is some interaction between AI and data science, but one is not a subset of the other. Rather, data science is a broad term that encompasses the entire data processing methodology, while AI includes everything that allows computers to learn how to solve problems and make intelligent decisions. Both AI and data science can involve the use of big data, that is, significantly large volumes of data.
Welcome to Generative AI and Data Science. After watching this video, you'll be able to describe generative AI and explain how data scientists use generative AI in data science. Generative AI is a subset of artificial intelligence that focuses on producing new data rather than just analyzing existing data. It allows machines to create content including images, music, language, computer code, and more, mimicking creations by people. How does generative AI operate, though? Deep learning models like generative adversarial networks, or GANs, and variational autoencoders, VAEs, are at the foundation of this technique. These models create new instances that replicate the underlying distributions of the original data by learning patterns from enormous volumes of data. Generative AI has found diverse applications across various industries. Let's look at some fascinating examples. Natural language processing like OpenAI's GPT-3 can generate human-like text, revolutionizing content creation and chatbots. In healthcare, generative AI can synthesize medical images, aiding in the training of medical professionals. Generative AI can create unique and visually stunning artworks, generating endless creative visual compositions. Game developers use generative AI to generate realistic environments, characters, and game levels. Generative AI assists in fashion by designing new styles and creating personalized shopping recommendations. Now, let's discuss how data scientists use generative AI. Training and testing a model takes a lot of data. Sometimes, the data you want to study doesn't have enough observations to build a model. Interest in synthetic data as a tool for analysis and model creation has increased due to the recent developments in generative AI. Data scientists can augment their data sets using generative AI to create synthetic data. It creates this data with similar properties as the real data, such as its distribution, clustering, and many other factors the AI learned about the real data set. Data scientists can then use the synthetic data along with real data for model training and testing. Data scientists, researchers, and analysts frequently find themselves confined by time when examining data patterns and insights. Due to this restriction, they can only conceive, develop, and evaluate a small number of hypotheses, leaving many other possibilities untested. With generative AI, data scientists can leverage generative AI to generate and test software code for constructing analytic models. Coding automation has the potential to revolutionize the field of analytics, allowing the data scientist to focus on higher-level tasks, such as identifying and clarifying the problem the models intend to solve, and evaluating hypotheses from a wider range of data sources. Generative AI can generate accurate business insights and comprehensive reports, making it possible to update these insights as the data evolves. Furthermore, it can autonomously explore data to uncover hidden patterns and insights that might go unnoticed during manual analysis and enhance decision-making. For instance, IBM's Cognos Analytics, which provides AI-powered automation, enables you to unlock the full potential of your data with the help of its natural language AI assistant. You describe the question you're looking to answer or the hypothesis you want to test, and it helps generate the insights you need. In this video, you learned that generative AI, a subset of artificial intelligence, focuses on producing new data rather than analyzing existing data. Generative AI augments data science efforts, enabling deeper insights, addressing data limitations, and improving the overall quality of data-driven outcomes.
It's, I guess, computer science's attempt to mimic the neurons and how our brain actually functions. So 20, 30 years ago, a neural network would have some inputs that would come in. They would be fed into different processing nodes that would then do some transformation on them and aggregate them or something, and then maybe go to another level of nodes. And finally, some output would come out. And I can remember training a neural network to recognize digits, handwritten digits and stuff. So a neural network is trying to use a computer program that will mimic how our brains use neurons to process things, neurons to synapses, and building these complex networks that can be trained. So a neural network starts out with some inputs and some outputs, and you keep feeding these inputs in to try to see what kinds of transformations will get to these outputs. And you keep doing this over and over and over again in a way that this network should converge, so the transformations will eventually get these outputs. Problem with neural networks was that even though the theory was there, and they did work on small problems, like recognizing handwritten digits and things like that, they were computationally very intensive. And so they went out of favor, and I stopped teaching them, probably 15 years ago. And then, all of a sudden, you started hearing about deep learning. I heard the term deep learning. This is another term that, when did you first hear it? 4 years ago, 5 years ago? And so I finally said, what the hell is deep learning? It's really doing all this great stuff. What is it? And I Googled it and I thought, well, this is neural networks on steroids. What they did was they just had multiple layers of neural networks, and they used lots and lots and lots of computing power to solve them. Just before this interview, I had a young faculty member in the marketing department whose research is partially based on deep learning. And so she needs a computer that has a graphics processing unit in it, because it takes an enormous amount of matrix and linear algebra calculations to actually do all of the mathematics that you need in neural networks. But they are now quite capable. We now have neural networks and deep learning that can recognize speech, can recognize people. If you're out there, and getting your face recognized, I guarantee that NSA has a lot of work going on in neural networks. The university right now, as director of research computing, I have a small set of machines down at our South Data Center. And I went in there last week, and there were just piles and piles and piles of cardboard boxes, all from Dell with a GPU on the side. Well, the GPU is a graphics processing unit. There's only one application in this university that needs 200 servers, each with graphics processing units in it, and each graphics processing unit has the equivalent of 600 cores of processing. So this is tens of thousands of processing cores. That is for deep learning, I guarantee. Some of the first ones are speech recognition. Jan LeCun, who teaches the deep learning class at NYU and is also the head data scientist at Facebook, comes into class with a notebook, and it's a pretty thick notebook. It looks a little odd because it's like this, and it's that thick because it has a couple of graphics processing units in it. And then he will ask the class to start to speak to this thing, and it will train while he's in class. He will train a neural network to recognize speech. So recognizing speech, recognizing people, images, classifying images, almost all of the traditional tasks that neural nets used to work on in little tiny things, now they can do really, really, really large things. It will learn on its own the difference between a cat and a dog and different kinds of objects. It doesn't have to be taught. It just learns. That's why they call it deep learning. And if you hear, he plays this, if you hear how it recognizes speech and generates speech, it sounds like a baby learning to talk. Right? You're like, all of a sudden this stupid machine is talking to you and learned how to talk. That's cool. You need to learn some linear algebra. A lot of this stuff is based on matrix and linear algebra, so you need to know how to use linear algebra to do transformations. Now, on the other hand, there's now lots of packages out there that will do deep learning, and they'll do all the linear algebra for you, but you should have some idea of what is happening underneath. Deep learning in particular needs really high-powered computational power. So it's not something that you're going to go out and do on your notebook, or you could play with it, but if you really want to do it seriously, you have to have some special computational resources. Everybody now deals with machine learning, but recommender systems are certainly one of the major applications. Classifications, cluster analysis, trying to find some of the marketing questions from 20 years ago, market basket analysis, what goods tend to be bought together. That was computationally a very difficult problem. I mean, we're now doing that all the time with machine learning. So predictive analytics is another area of machine learning where we're using new techniques to predict things that statisticians don't particularly like. decision trees, Bayesian analysis, naive Bayes, lots of different techniques. The nice thing about them is that in packages like R now, you really have to understand how these techniques can be used, and you don't have to know exactly how to do them, but you have to understand what their meanings are. Precision versus recall, and how, the problems of oversampling and overfitting. So you can, someone who knows a little bit about data science can apply these techniques, but they really need to know maybe not the details of the technique as much as how, what the trade-offs are.
So some applications of machine learning in fintech are probably a couple of different things I can talk about there. One of them is recommendations, right? So when you use Netflix or you use Facebook or a lot of different software services, the recommendations are served to you, meaning, hey, you're a user, you've watched this show, so maybe you'd like to see this other show, right? Or you follow this person, so maybe you should follow that other person. It's actually kind of the same thing in fintech, right? Because you've looked at, if you're an investment professional, right? And because you've looked at this investment idea, it might be really cool for you to look at this other investment idea, which is kind of similar, right? It's a similar kind of asset, or it's a similar kind of company, or it's a similar kind of technique for doing the investment. So we can apply recommendations using machine learning throughout a lot of different parts of fintech. Another one that people talk about and is important, especially on retail, in the retail aspects of banking and finance, is fraud detection. Trying to determine whether a charge that comes through a credit card is fraudulent or not in real time is a machine learning problem, right? You have to learn from all of the transactions that have happened previously and build a model. And when the charge comes through, you have to compute all this stuff and say, yeah, we think that's okay, or that's not so good. Let's route it to, our fraud people to kind of check.
Welcome to the Deep Learning and Machine Learning Lesson Summary. In this video, we'll review what you learned about deep learning and machine learning from the videos and readings in this lesson. We will recap many of the terms commonly used in artificial intelligence and how to differentiate them, how data scientists use artificial intelligence or AI, the relationship between machine learning and data science, and the regression model used to show relationships between things. Artificial intelligence, or AI, has boomed and become accessible to almost everyone. Data scientists use AI regularly when analyzing data. Let's discuss some of the terms used in this lesson related to AI, such as machine learning, deep learning, neural networks, and generative AI. AI is the branch of computer science that includes the development of systems that can mimic many of the tasks associated with human intelligence. Machine learning is a subset of AI that uses computer algorithms to learn about data and make predictions with it, without needing to explicitly program the analysis methods into the system. Deep learning is a subset of machine learning that uses layered neural networks to simulate human decision-making. A neural network is a collection of small computing units, called neurons, that take incoming data and learn to make decisions over time, such as the difference between a dog and a cat. Deep learning algorithms become more efficient as the amount of data increases in volume, unlike other machine learning algorithms, which tend to plateau. Another subset of AI, generative AI, focuses on producing new data rather than just analyzing existing data. It allows machines to create content including images, music, languages, and computer code, mimicking human creations. Generative AI also can make data sets with similar traits to a raw data set. Sometimes data scientists, when they do not have enough data, can create synthetic data and use it to train and test their models. As a data scientist, you will use machine learning algorithms to derive insights from data. You will frequently apply machine learning algorithms for predictive analytics or make recommendations. For example, you may also use these algorithms for fraud detection to identify fraudulent credit card purchases based on previous purchasing habits. Machine learning algorithms rely heavily on statistical technique called regression. Regression identifies the strength and amount of a correlation between one or more inputs and an output. For instance, how much does the price of a house increase based on its square footage and number of bedrooms, and how confident can you be of this relationship? In summary, generative AI produces new data like a raw data set. Deep learning is a subset of machine learning, and machine learning is a subset of artificial intelligence. Deep learning utilizes neural networks to teach itself patterns and inputs and outputs. Using big data, data scientists use all of these areas of AI to make predictions.
At the end of the day, for businesses, they know one thing, that if they are unable to measure something, they are unable to improve it. And if they're unable to measure their costs, they are unable to reduce them. If they're unable to measure their profits, they're unable to increase them. So the first thing a company has to do is to start recording information, start capturing data. Data about costs, data about and then differentiated by labor costs and material costs, the cost to how much it costs to sell one product, and the total cost. And then you look at the revenue. Where is your revenue coming from? Is your 80% of your revenue coming from 20% of your customers, or is it the other way around? So first thing first, start capturing data. Once you have data, then you can apply algorithms and analytics to it. So the first thing to do would be to capture data. If you're not capturing it, start capturing it. If you're capturing it, archive it. Do not overwrite on your old data thinking you don't need it anymore. Data never gets old. Data is always relevant. Even if it's 100 years old, 200 years old, it is relevant to you and your firm and your success. So keep data, capture it, archive it, make sure nothing goes to waste, make sure there's a consistency, so someone 20 years later trying to understand that data should be able to do so. So have proper documentation, do it now, put the best practices for data archiving in place the moment you start a business. And if you're already in business and you haven't done it, do it now.
Start measuring things. Too many companies haven't measured things properly for a decade, and then they decide they want data science. Data science and inside a company is only going to be as valuable as the data collected. Garbage in, garbage out is a rule in any sort of analysis.
If something is not measured, it's very difficult to improve it or to change it. So the very first step is measurement. If companies have existing data, then they should start looking at it and cleaning it. If they don't have existing data, then they need to start collecting it.
I think to look for a team who love to work as a data scientist.
I think that the first step is to have employees that they are interested on data science, because if you don't have interest in your company, you will not have engagement.
Companies should remember that it's key to have a team, so it's not one data scientist, but a team of them, that each of them have strengths in different areas of data science.
Organizations can leverage the almost unlimited amount of data now available to them in a growing number of ways. However, all organizations ultimately use data science for the same reason: to discover optimum solutions to existing problems. Let's take a look at 3 examples of data science providing innovative solutions for old problems. In transport, Uber collects real-time user data to discover how many drivers are available, if more are needed, and if they should allow a surge charge to attract more drivers. Uber uses data to put the right number of drivers in the right place at the right time for a cost the rider is willing to pay. In a different transport-related data science effort, the Toronto Transportation Commission has made great strides in solving an old problem with traffic flows, restructuring those flows in and around the city. Using data science tools and analysis, they have gathered data to better understand streetcar operations and identify areas for interventions, analyzed customer complaints data, used probe data to better understand traffic performance on main routes, and created a team to better capitalize on big data for both planning, operations, and evaluation. By focusing on peak hour clearances and identifying the most congested routes, monthly hours lost for commuters due to traffic congestion dropped from 4.75 hours in 2010 to 3 hours in mid-2014. In facing issues in our environment, data science can also play a proactive role. Freshwater lakes supply a variety of human and ecological needs, such as providing drinking water and producing food. But lakes across the world are threatened by increasing incidences of harmful cyanobacterial blooms. There are many projects and studies to solve this long-existing dilemma. In the U.S., a team of scientists from research centers stretching from Maine to South Carolina is developing and deploying high-tech tools to explore cyanobacteria in lakes across the East Coast. The team is using robotic boats, buoys, and camera-equipped drones to measure physical, chemical, and biological data in lakes where cyanobacteria are detected, collecting large volumes of data related to the lakes and the development of the harmful blooms. The project is also building new algorithmic models to assess the findings. The information collected will lead to better predictions of when and where cyanobacterial blooms take place, enabling proactive approaches to protect public health in recreational lakes and in those that supply drinking water. Such interdisciplinary training prepares the next generation of scientists to address societal issues with the proper modernized data science tools. It takes gathering a lot of data, cleaning and preparing it, and then analyzing it to gain the insight needed to develop better solutions for today's enterprises. How do you get a better solution that is efficient? You must identify the problem and establish a clear understanding of it. Gather the data for analysis, identify the right tools to use, and develop a data strategy. Case studies are also helpful in customizing a potential solution. Once these conditions exist and available data is extracted, you can develop a machine learning model. It will take time for an organization to refine best practices for data strategy using data science, but the benefits are worth it.
Data science and big data are making an undeniable impact on businesses, changing day-to-day operations, financial analytics, and especially interactions with customers. It's clear that businesses can gain enormous value from the insights data science can provide, but sometimes it's hard to see exactly how, so let's look at some examples. In this era of big data, almost everyone generates masses of data every day, often without being aware of it. This digital trace reveals the patterns of our online lives. If you have ever searched for or bought a product on a site like Amazon, you will notice that it starts making recommendations related to your search. This type of system, known as a recommendation engine, is a common application of data science. Companies like Amazon, Netflix, and Spotify use algorithms to make specific recommendations derived from customer preferences and historical behavior. Personal assistants like Siri on Apple devices use data science to devise answers to the infinite number of questions end users may ask. Google watches your every move in the world, your online shopping habits, and your social media. Then it analyzes that data to create recommendations for restaurants, bars, shops, and other attractions based on the data collected from your device and your current location. Wearable devices like Fitbits, Apple Watches, and Android watches add information about your activity levels, sleep patterns, and heart rate to the data you generate. Now that we know how consumers generate data, let's take a look at how data science is impacting business. In 2011, McKinsey & Company said that data science was going to become the key basis of competition, supporting new waves of productivity, growth, and innovation. In 2013, UPS announced that it was using data from customers, drivers, and vehicles in a new route guidance system aimed to save time, money, and fuel. Initiatives like this support the statement that data science will fundamentally change the way businesses compete and operate. How does a firm gain a competitive advantage? Let's take Netflix as an example. Netflix collects and analyzes massive amounts of data from millions of users, including which shows people are watching at what time of day, when people pause, rewind, and fast forward, and which shows, directors, and actors they search for. Netflix can be confident that a show will be a hit before filming even begins by analyzing users' preference for certain directors and acting talent, and discovering which combinations people enjoy. Add this to the success of earlier versions of a show, and you have a hit. For example, Netflix knew many of its users had streamed the work of David Fincher. They also knew that films featuring Robin Wright had always done well, and that the British version of House of Cards was very successful. Netflix knew that significant numbers of people who liked Fincher also liked Wright. All this information combined to suggest that buying the series would be a good investment for the company. They were right, it was a huge hit. Thanks to data science, Netflix knows what people want before they do. Using data science techniques to understand and analyze the large data sets available today has a huge impact on human lives. It can provide targeted information to help healthcare professionals give the best treatment to patients, or help predict natural disasters so that people can prepare early, and much more besides. In healthcare, data scientists use predictive analytics developed from data mining, data modeling, statistics, and machine learning to find the best options for patients. This type of predictive analytics examines all known factors for a disease, including gene markers, associated conditions, and environmental factors. It then recommends appropriate tests, suitable trials, and any suggested treatments. Every individual physician has their own store of knowledge gained from their studies, interests, and experiences. Data science systems that use predictive analytics ensure that all physicians can also access the latest information about the disease, tests, and treatment plans tailored to their specific patient. With this type of system, every physician has access to the same knowledge, and the best options can be consistently offered, improving patient outcomes. For example, a study by the Boston Consulting Group and AdvaMed DX, an industry association of medical diagnostics companies, examined the barriers to the adoption of potentially life-saving diagnostic tests for patients with a specific cancer and a particular gene marker. The study discovered that the biggest factor in the patient being offered a specific test was the patient's oncologist, who may or may not have known about the test and its relationship to the gene marker. By providing extra information through data science tools, physicians can be made aware of the most helpful tests and treatments for a specific patient. There are many opportunities to explore other ways to mine data, such as from electronic medical records for different types of medical research. Schools such as the North Shore University Health System in suburban Chicago, a leader in the implementation of electronic medical records, EMR systems, now offer guidance on data mining. It is the first healthcare provider in America to be awarded the highest level of EMR deployment for both inpatient and outpatient care. This remarkable effort has generated much anonymized data available for innovative analytics research. Developing more sophisticated big data analytics capabilities helps healthcare organizations move from basic descriptive analytics towards predictive insights thanks to data science. In the field of disaster preparedness, the ability to save lives using data science tools has been under development for many years. The use of predictive analytics tools is improving and providing new data analysis in a multitude of ways, alerting populations to danger faster than ever before. Large, high-quality datasets can be used to predict the occurrence of numerous types of natural disasters, which can be the difference between life and death for thousands of people. Earthquakes, hurricanes and tornadoes, floods, and volcanic eruptions can be predicted with the help of data science. Recent research at the University of Warwick in the UK used social media content such as photos and keywords
to track the development of floods, hurricanes, and other weather events. When added to the information recorded by scientists and weather stations, this type of data can be used to improve the predictions for localized weather events. Because the real benefit of this knowledge is so important, schools are starting to include this type of data science education in their curriculum. For instance, the University of Chicago Graham School offers a Master of Science course in Threat and Response Management. Data science tools enable organizations to analyze vast quantities of data from widely different sources and present that information in a way that allows data scientists to gain new knowledge, in some cases, saving hundreds of lives.
Welcome to the Data Science Application Lesson Summary video. In this video, let's review what you've learned in this lesson about the power of data science applications and how organizations leverage this power to drive business goals, improve efficiency, make predictions, and even save lives. You also reviewed the process that you will follow as a data scientist to help your organization accomplish these ends. All organizations ultimately use data science for the same reason: to discover optimal solutions to existing problems. But to discover these solutions, your organization should identify the problem and establish a clear understanding of it. Measurement is the first step for an organization to solve its problem using data. You need to capture and gather your data. If something is not measured, it's challenging to improve or change it. If your organization isn't capturing the data, help them to figure out how to capture it. Never overwrite old data. It's always relevant and never gets old. Once you have the data, you can start looking at it and cleaning it. As a data scientist, it's your job to help your organization identify tools and develop an analysis strategy. Consider case studies when customizing a potential solution. Identify your analysis tools, and then develop your machine learning and statistical models. It will take time for your organization to refine data strategy best practices, but the benefits are worth it. Everyone who uses the internet generates mass amounts of data daily, often without being aware of it. Your company can leverage that data to reveal patterns. Take, for instance, a company like Amazon. You'll notice that it starts making recommendations related to your search. That's called a recommendation engine. Data scientists build those engines using machine learning and statistical models. Companies like UPS use data science to inform their business decisions. They use data from customers, drivers, and vehicles to create routes for their drivers, making more efficient use of the driver's time, money, and fuel. Uber uses data to put the correct number of drivers in the right place at the right time, for a price the rider is willing to pay. Initiatives like this show how data science fundamentally changes how businesses compete and operate. Businesses also use data science to gain competitive advantages. Take streaming companies as an example. They collect and analyze massive amounts of data from millions of users, including which shows they watch and what time of day. They detect when people pause, rewind, and fast forward. They collect information such as which directors and actors they search for. A streaming company can confidently predict the success of a show before filming begins by thoroughly analyzing its users' preferences and behaviors. Beyond helping businesses with their bottom line, data science helps companies and organizations save lives. In healthcare, data scientists use predictive analytics developed from data mining, data modeling, statistics, and machine learning to find the best option for patients. This type of predictive analytics examines factors for a disease, including gene markers, associated conditions, and environmental factors. Data scientists use their models to help physicians recommend appropriate tests, suitable trials, and suggest treatments. Developing more extensive data analytics capabilities supports healthcare organizations' move from basic descriptive analytics towards predictive insights, thanks to data science. Data science tools enable organizations to analyze vast amounts of data from various sources. Large, high-quality data sets can help predict the occurrence of natural disasters such as earthquakes, hurricanes, tornadoes, floods, and volcanic eruptions. The data scientists present that information in a way that allows organizations to gain new understandings and, in some cases, save lives. When presenting your findings, you will provide your organizations with a final deliverable that explains and summarizes their conclusions. In academia, the final deliverable comprises research papers and reports. You often present the final deliverable illustrated with tables and plots in consulting and business. You will generate analytics-driven reports to communicate your findings to your organization and, in the process, establish powerful, convincing, and evidence-based narratives.
A real data scientist, the high-end data scientists are mostly PhDs. They often come out of physics, out of statistics. They have to have computer science background, they have to have a math background, they have to know about databases and statistics and probability and all that stuff. However, if you're coming into a data science team, I think that the first skills you need is you need to know how to program, at least have some computational thinking. So you've had to have taken a programming course. You need to know some algebra, at least up to analytics geometry, and hopefully some calculus. Some basic probability, some basic statistics. I mean, you really have to understand statistical inference and different statistical distributions, and database. I mean, one of the easiest places to start is relational databases, which stores lots and lots of our data. So people can first walk before they can run by at least understanding about computers and databases and how we store things. And if you understand relational databases, nowadays you can still, just with that understanding, use big data clusters as if they were just a big relational database. You don't have to really understand the whole MapReduce programming model. But then, as you go further up in the field, then you have to know a lot of computer science theory and statistics. It's really, and probability. It's really the intersection of them that the high-end data scientists, the PhD data scientists, work with. I do a lot of self-learning. I think everybody these days, I mean, I learned about Hadoop all by myself. I read some articles, I watched some videos, I thought, I played. Although I'm a builder, I'm a tinkerer. So when I really want to, if I want to figure out how to do something, I build it. I mean, my first HPC cluster, I'd heard about this term, a Beowulf cluster. And again, I'm like, what the hell's that? So I looked it up and said, oh, that's just a bunch of computers hooked together with a TCP/IP network. That's pretty easy. So we got a grant from Citibank, and we built a five-thing cluster. And I said, oh, that's HPC. So I had one of the first HPC clusters at the university. It was tiny, but a lot of our researchers loved it because they could run stuff 40 and 50 times faster. So I think one of the ways you learn things is you do them. You have to do them. And these online learning platforms, especially now that we have things like IPython and Jupyter Notebooks and I guess Zeppelin, means that you can actually go in and take some of these courses and you can do things right then. And you can see them and feel them and play with them. And at that point, you start to get your head around what is actually happening. Motivation is the key problem in all of these, is how to keep people motivated and how, and I think the badge system that that the Big Data University has is one of the ways. Is how do you get people to keep going through? But if they want to, they can't. Right? It's up to the individual too. So they have to understand what the goal is. The place it can't sit is probably under the CIO, the Chief Information Officer. CIOs, current Chief Information Officers in many companies, got there from an accounting background or a finance background. They're clueless. Sorry, but I mean, it has to come out of the research side, right there. So you'll find data scientists primarily in companies that have some research agenda, pharmaceuticals, finance, all of any technology company. If you look at, we can't keep some of our PhD data scientists in our program. They're now at Facebook, they're at LinkedIn, they're at Uber, they're at Lyft, because the demand out there for the PhD level data scientists is just unbelievable. They make large amounts of money and they're playing with problems that are really, really neat. Like, how do you schedule the Uber cars? Right? And you have enormous amounts of data.
When the companies are hiring people for a data science team, may it be a data scientist or an analyst or a chief data scientist, the tendency would be to find the person who has all the skills, that they know the domain-specific knowledge, they're excellent in analyzing structured and unstructured data, and they're great at presenting, and they've got the great storytelling skills. So if you put all this together, you will realize you're looking for a unicorn, and your odds of finding a unicorn are pretty rare. I think what you need to do is to see, given the pool of applicants you have, who has the most resonance with your firm's DNA. Because see, you can teach analytic skills. Anyone can learn analytic skills if they would dedicate time and effort to it. But what really matters is who is passionate about the kind of business that you do. Someone could be a great data scientist in a retail environment, but they may not be that excited about working in IT related firms or working with gigabytes of weblogs. But if someone is excited about those weblogs, or someone is excited about health related data, then they would be able to contribute to your productivity much more so. And I would say, if I'm looking for someone, if I have to put together a data science team, I would first look for curiosity. Is that person curious about things, not just for data science, but anything? Like, are they curious about why this room is painted a certain way, why the bookshelves have books and what kind of books? They have to have certain degree of curiosity about everything that is in their vision, that they look at. The second thing is, do they have a sense of humor? Because you see, you have to have a lighthearted about it. If someone is too serious about it, they probably would take it too seriously and would not be able to look at the lighter elements. The third thing, I think, and I think the last thing that I would look for, if I have to have a hierarchy, the last thing I would look for are technical skills. I would go through these social skills, curiosity, sense of humor, the ability to tell a story, the ability to know that there is a story there. And then once all is there, then I will say, well, can you do the technical side of it? And if there's some hope or some sign of some technical skills, I would take them, because I can train them in whatever skills they need. But I cannot teach curiosity, I cannot teach storytelling, I cannot certainly instill sense of humor in anyone.
I think there's no hard and fast rule for hiring data scientists. I think it's going to be a case-by-case thing. I would say there has to be some sort of technical component. Somebody should be able to work with and manipulate the data. They should be able to communicate what they find in the data. I find quite often nobody really cares about the R-squared or the confidence interval, so you have to be able to introduce those things and explain something in a compelling way. And they also have to find somebody who is relatable, because data science, it being typically new, means that the person in that role has to make relationships and they have to work across different departments.
If these data scientist has a good mathematics and statistics background,
they have to consider like problem-solving abilities and analysis. A data scientist needs to be good in analyzing problems.
The persons they are hiring, they should love to play with data, and then they know how to play with the data, visualization, they have analytical thinking.
When a company is hiring anyone to work on a data science team, they need to think about what role that person is going to take. Before a company begins, they need to understand what they want out of their data science team, and then they need to hire to begin it. As they grow a data science team, they need to understand whether they need engineers, architects, designers to work on visualization, or whether they just need more people who can multiply large matrices.
From a skills point of view, let's focus on the technical skills. And in that case, first thing would be, what kind of a technical platform would you like to adopt? Let's say you want to work in a structured data environment, and let's say you want to work in market research. Then the type of skills you need are slightly different than someone who would like to work in big data environments. If you want to work in the traditional market research data, structured data environment, your skills should be some statistical knowledge, some knowledge of basic statistical algorithms, maybe some machine learning algorithms, and these are the tools that you would like to develop. If you want to work in big data, then there's the other aspect of it, and that is to be able to store data. So you start with the expertise in storing large amounts of data, and then you look into platforms that allow you to do that. The next step would be to be able to manipulate large amounts of data, and the final step would be to apply algorithms to those large sets of data. So it's a three-step process, but most likely it starts, most importantly, it starts with where you would like to be, in what field, in what domain. So in terms of platforms, let's say you want to be in a traditional predictive analytics environment, and you're not working with big data, then R or Stata or Python would be your tools. If you're working mostly with unstructured data, then Python is more suitable than R. If you're working with big data, then Hadoop and Spark are the environments that you would be working with. So it all depends upon where you would like to be and what kind of work excites you, and then you pick your tools. In addition to technical skills, the second aspect of the data science is to have the ability to communicate, the communication skills or presentation skills. I call them storytelling skills. That is, that you have your analysis done. Now, can you tell a great story from it? If you have a very large table, can you synthesize it and make it more appealing, that when it goes on the screen, or is it part of a document that it just speaks, it sings the findings, and the reader just gets it right there. So the ability to present your findings either verbally or in a presentation or in a document. So that communication and presentation skills are equally important as the technical skills are. When you have a great insight and when you're presenting your results, imagine you're driving on a mountain, and then there's a sharp turn, and you can't see what's beyond the turn, and then you make that turn, and then suddenly you see a tremendous valley in front of you, and there's this great sense of awe that I didn't know that, right? So when you present your findings and you have this great finding and you communicate it well, this is what people feel, because they were not expecting it, they were not aware of it, and then this great sense of happiness that now I know. And I didn't know this, now I know. And then it empowers them, it gives them ideas what they can do with this knowledge, this new insight. It's a great sense of joy. And you are able to, as a data scientist, you're able to share it with your clients because you enabled it.
The emergence of Internet of Things and advances in distributed computing have brought vast amounts of data and the technological capability to analyze it. Now that we can extract useful insights and new knowledge, we need to know how to shape that data to focus on what to do with it and what it can do for us. Enter data science. Companies like LinkedIn, Glassdoor, Indeed, and Dice track employment trends which show a career in data science moving up the list of most promising jobs to become number 1 since 2016. It remains one of the top 3 career choices for 2020. Dice noted that job postings are from companies in a wide variety of industries, not just tech. Global Industry Analysts Incorporated predicts that the data science platform market will grow by $314.8 billion by 2025, driven by a compounded growth of 38.2%. McKinsey Global Institute warned of huge talent shortages for data and analytics by 2018. Forrester research analyst Brandon Purcell said in January of 2019, the demand for data scientists will only grow as organizations increasingly rely on data-driven insights. We're now well into that period, and recruiters are finding it difficult to fill the growing need for talented data scientists. What motivates someone going into a data science career?
For one thing, data science applies to almost any discipline. So, if you have the aptitude and desire to work with data, enjoy coding, have no problem learning math and statistics, and you are a good storyteller, then you can certainly enter a data science field and excel. For most people, this means acquiring additional tools and skills and continuously learning about new tools and techniques in the field. The Women in Data Science Initiative, spearheaded by the Stanford Institute for Computational and Mathematical Computing, have committed to inspire and educate data scientists worldwide, regardless of gender, and to support women in the field. When you are seeking a career in data science, you need to make sure your skill set matches the role you are targeting. You can tailor your skill set to the specific area you want to enter, adding missing skills via one of the many excellent online training resources. Then you'll be prepared for a fascinating and rewarding career. So now it is time to move into this field when there are such diverse choices available and education resources that make it a reality.
Learn how to program, learn some math, take a course in probability, learn a little bit of statistics, and then play. Build something. Write something. I mean, when I say build, programming and building systems, building things isn't just physical, right? You can build computer systems, statistical systems, whatever. But once you try to do something, and then you'll know what tools you need, right? And you'll say, oh my God, there's this expression there. What does an inner product mean? And what's that? Okay, I can learn that. And then when they get to college, they will have a big jump on many of the other college students. And so when they get out of college, they'll have an even bigger jump and they'll make a lot of money. And they'll be happy too. This stuff is fun, right? It's fun.
If you're in high school and you're considering data science, I would say get familiar with databases. Start learning SQL. Start thinking about, computer science if that's interesting. If you have a computer science course in your school, take it. And that's a good part of being a data scientist. Beyond that, there are probably just ways to foster your creativity, right? Your curiosity. If you like detective games, that's kind of cool, right? If you like, treasure hunts or whatever, right? If you're into that stuff, I think you'll and you get an opportunity to do that stuff, that will help you as a data scientist, because it's a really a good way to kind of make sure that you can be curious as you go about, your daily life. Encourage the curiosity, encourage the experimentation. It's kind of like science fairs, right? Science fairs are great, and they encourage that experimentation, that learning from, asking a question and answering it through a scientific method, but doing that with, data sets rather than vinegar volcanoes, right? It's kind of the same thing, but learning from data. And if we're going through an election season right now, there's a lot of stuff in the news about polls and survey results, and that's a great way to start a conversation, to talk about how did the people who ran the polls, how did they know, how can they predict what's going to happen in the election? And so that's another kind of cool way to start a conversation about data science. I would say encourage the person who is interested in data science to pursue it, because it's a great career, and it's something that's definitely going to be in need in the future. It's one of those highly sought after kind of knowledge professions that are really important to businesses around the world, so being a data scientist and being able to help companies as they grow and learn how to do things more efficiently or how to do things smarter. There'll always be a need for people like that, and data scientists are those people. I would say that I understand what you're talking about because I was never a great mathematics student as well. And I think there's actually a bunch of data scientists who are really successful and popular who are in the same boat. You know, there's kind of arithmetic and math in school is not necessarily everybody's best subject. But when you combine it with, you know, these aren't just, you know, hypothetical numbers. These aren't just, you know, problem statements that you have no connection to. When you have a connection to the problem, it suddenly becomes much easier to use math to help understand it, I've found. And so, you know, knowing the people who will benefit from the math that you do, I think is really cool.
Welcome to the Careers and Recruiting in Data Science lesson summary video. In this lesson, you investigated what companies seek in a competent, experienced data scientist. You learned how to position yourself to get hired as a data scientist. Amidst the diverse backgrounds from which data scientists emerge, you also find they share qualities and skills that consistently set them apart from other data-related roles. Companies recruiting data scientists may seem to want data scientists to have it all. They may seek a person who has all the desired skills, ranging from domain-specific knowledge to proficiency in analyzing both structured and unstructured data, as well as skills in presenting and storytelling. Realistically, this person is a rare find. Instead, companies need to develop teams of people who work together who have these skills rather than seeking out individuals who have all of these qualities. They also may need to seek out individuals with potential and help them develop the skills they need. What really matters is they find someone passionate about the kind of business that they do. Companies should look for someone excited about working with the data in their particular industry. They should seek out someone curious who can ask interesting, meaningful questions about the types of data they intend to collect. For example, a person who could be a great data scientist in the retail environment may not be excited about working in IT-related firms or working with gigabytes of health-related weblogs. Companies will find that excitement results in high productivity. That excitement also relates back to curiosity, which we discussed in another lesson, as an important trait for a data scientist. Someone excited about their field is likely to be curious and find the right questions to ask. Constantly wondering why things are the way that they are helps you stay motivated and engaged. Similarly, self-learning and tinkering are also helpful traits. As a data scientist, you should love to play with data and create data visualizations. You need to think analytically and computationally. You need a strong background in mathematics, statistics, and probability to reach valid conclusions with that data. You also need computer programming skills. Tools may vary with the type of data that you'll work with. Though common languages include Python and R, an open-source programming language developed for statistical analysis. Because data scientists work with large quantities of stored data, you must also understand data storage and retrieval systems with structured and unstructured data. With artificial intelligence, you also need to know common machine learning algorithms to gain insights from their data. One or more persons from the data science team at an organization will write a report as the final step of the analysis. So, communication, instructional and presentational skills, and storytelling skills are also important. The report synthesizes these large amounts of data to create a narrative that engages and surprises the reader. A clearly organized and logical report should communicate the following to the reader: what they gained by reading the report, clearly defined goals, the significance of your contribution, appropriate context by giving sufficient background, why this work is practical and useful, and conjugate plausible future developments that might result from your work. As Dr. Hayter explained, imagine your reader is driving on a mountain. There's a sharp turn ahead and they can't see what's beyond the turn. They go around the curve and suddenly they see a tremendous valley in front of them. They experience this great sense of awe. So, when you were presenting this great finding and communicating it well, this is what people feel because they were not expecting it. In summary, companies need to look for individuals to create a data science team and be cautious about trying to find all the desired skills in a single individual. On that team, they should have curious people who understand the subject matter well, people who love working with the data, and those with statistics, mathematics, machine learning, and computer programming expertise. Lastly, and possibly most importantly, they need a skilled storyteller who can present the team's findings in a creative and engaging way.
Data is unorganized information that is processed to make it meaningful. Generally, data comprises of facts, observations, perceptions, numbers, characters, symbols, and images that can be interpreted to derive meaning. One of the ways in which data can be categorized is by its structure. Data can be structured, semi-structured, or unstructured. Structured data has a well-defined structure or adheres to a specified data model, can be stored in well-defined schemas such as databases, and in many cases can be represented in a tabular manner with rows and columns. Structured data is objective facts and numbers that can be collected, exported, stored, and organized in typical databases. Some of the sources of structured data could include SQL databases and online transaction processing, or OLTP, systems that focus on business transactions, spreadsheets such as Excel and Google Sheets, online forms, sensors such as global positioning systems, or GPS, and radio frequency identification, or RFID tags, and network and web server logs. You can also easily examine structured data with standard data analysis tools and methods. Semi-structured data is data that has some organizational properties but lacks a fixed or rigid schema. Semi-structured data cannot be stored in the form of rows and columns, as in databases. It contains tags or elements or metadata, which is used to group data and organize it in a hierarchy. Some of the sources of semi-structured data could include emails, XML and other markup languages, binary executables, TCP or IP packets, zippered files, and integration of data from different sources. XML and JSON allow users to define tags and attributes to store data in a hierarchical form and are used widely to store and exchange semi-structured data. Unstructured data is data that does not have an easily identifiable structure and therefore cannot be organized in a mainstream relational database in the form of rows and columns. It does not have any particular format, sequence, semantics, or rules. Unstructured data can deal with the heterogeneity of sources and has a variety of business intelligence and analytics applications. Some of the sources of unstructured data could include web pages, social media feeds, images in varied file formats such as JPEG, GIF, and PNG, video and audio files, documents and PDF files, PowerPoint presentations, media logs, and surveys. Unstructured data can be stored in files and documents, such as a Word document, for manual analysis, or in NoSQL databases that have their own analysis tools for examining this type of data. To summarize, structured data is data that is well organized in formats that can be stored in databases and lends itself to standard data analysis methods and tools. Semi-structured data is data that is somewhat organized and relies on meta tags for grouping and hierarchy. And unstructured data is data that is not conventionally organized in the form of rows and columns in a particular format. In the next video, we will learn about the different types of file structures. As we touched upon in one of our previous videos, data sources have never been as dynamic and diverse as they are today. In this video, we will look at some common sources such as relational databases, flat files and XML datasets, APIs and web services, web scraping, data streams and feeds. Typically, organizations have internal applications to support them in managing their day-to-day business activities, customer transactions, human resource activities, and their workflows. These systems use relational databases such as SQL Server, Oracle, MySQL, and IBM DB2 to store data in a structured way. Data stored in databases and data warehouses can be used as a source for analysis. For example, data from a retail transaction system can be used to analyze sales in different regions, and data from a customer relationship management system can be used for making sales projections. External to the organization, there are other publicly and privately available data sets. For example, government organizations releasing demographic and economic data sets on an ongoing basis. Then there are companies that sell specific data. For example, point of sale data or financial data or weather data, which businesses can use to define strategy, predict demand, and make decisions related to distribution or marketing promotions, among other things. Such datasets are typically made available as flat files, spreadsheet files, or XML documents. Flat files store data in plain text format, with one record or row per line, and each value separated by delimiters such as commas, semicolons, or tabs. Data in a flat file maps to a single table, unlike relational databases that contain multiple tables. One of the most common flat file formats is CSV, in which values are separated by commas. Spreadsheet files are a special type of flat files that also recognize data in a tabular format, rows and columns. But a spreadsheet can contain multiple worksheets, and each worksheet can map to a different table. Although data in spreadsheets is in plain text, the files can be stored in custom formats and include additional information such as formatting, formulas, etc. Microsoft Excel, which stores data in an XLS or XLSX format, is probably the most common spreadsheet. Others include Google Sheets, Apple Numbers, and LibreOffice. XML files contain data values that are identified or marked up using tags. While data in flat files is flat or maps to a single table, XML files can support more complex data structures such as hierarchical. Some common uses of XML include data from online surveys, bank statements, and other unstructured data sets. Many data providers and websites provide APIs, or Application Program Interfaces, and web services, which multiple users or applications can interact with and obtain data for processing or analysis. APIs and web services typically listen for incoming requests, which can be in the form of web requests from users or network requests from applications, and return data in plain text, XML, HTML, JSON, or media files. Let's look at some popular examples of APIs being used as a data source for data analytics. The use of Twitter and Facebook APIs to source data from tweets and posts for performing tasks such as opinion mining or sentiment analysis, which is to summarize the amount of appreciation and criticism on a given subject, such as policies of a government, product, a service, or customer satisfaction in general. Stock market APIs used for pulling data such as share and commodity prices, earnings per share, and historical prices for trading and analysis. Data lookup and validation APIs, which can be very useful for data analysts for cleaning and preparing data, as well as for correlating data, for example, to check which city or state a postal or zip code belongs to. APIs are also used for pulling data from database sources, within and external to the organization. Web scraping is used to extract relevant data from unstructured sources, also known as screen scraping, web harvesting, and web data extraction, Web scraping makes it possible to download specific data from web pages based on defined parameters. Web scrapers can, among other things, extract text, contact information, images, videos, product items, and much more from a website. Some popular uses of web scraping include collecting product details from retailers, manufacturers, and e-commerce websites to provide price comparisons, generating sales leads through public data sources, extracting data from posts and authors on various forums and communities, and collecting training and testing datasets for machine learning models. Some of the popular web scraping tools include Beautiful Soup, Scrapey, Pandas, and Selenium. Data streams are another widely used source for aggregating constant streams of data flowing from sources such as instruments, IoT devices and applications, GPS data from cars, computer programs, websites, and social media posts. This data is generally time-stamped and also geotagged for geographical identification. Some of the data streams and ways in which they can be leveraged include stock and market tickers for financial trading, retail transaction streams for predicting demand and supply chain management, surveillance and video feeds for threat detection, social media feeds for sentiment analysis, sensor data feeds for monitoring industrial or farming machinery, web-click feeds for monitoring web performance and improving design, and real-time flight events for rebooking and rescheduling. Some popular applications used to process data streams include Apache Kafka, Apache Spark Streaming, and Apache Storm. RSS, or Really Simple Syndication Feeds, are another popular data source. These are typically used for capturing updated data from online forums and news sites where data is refreshed on an ongoing basis. Using a feed reader, which is an interface that converts RSS text files into a stream of updated data, updates are streamed to user devices. In this video, we will listen to several data professionals talk about their experience of working with varied data sources and types of data.
So you'd be surprised the different ways that data can come at you. I tend to be a relational database fan, and so I spend a lot of time with SQL. And using the power of SQL to deal with moving data from one place to another, to deal with structuring of data, to deal with all the security details around data. But obviously, that doesn't apply to every scenario, and even when we're dealing entirely in relational databases, we're often moving data from one relational database to another, and especially when we're talking about one vendor to another, that can be challenging. The things that also get in the way tend to be the versioning. So sometimes the feature of something that you want is in a version 2 levels above where you are, or it doesn't work the same way as it did 2 versions ago. So working with multiple data sources is about flexibility. It's about finding the function that works and works with the performance you need. Moving data one time is usually not all that hard as long as we're sub-terabyte, but moving data consistently and continually and in a performant way can cause us to evaluate a lot of different solutions. So we really need to be open to new ideas and looking for new solutions that meet the requirements that we have.
Mostly I work with relational databases. They're extremely flexible and withstood the test of time. However, with the evolution of unstructured data such as logs, documents, XML, and JSON, their reputation as a cure for all of your data problems came under intense scrutiny. And most of data-intensive applications such as IoT and social media applications started to look elsewhere. For example, Google released a white paper back in 2006 called Google Big Table. And that idea quickly caught fire. For example, Cassandra and HBase came out of the same architectural model as the Google Big Table, and they became widely popular databases to solve some of the problems that relational databases fail to solve. For example, relational databases struggle a little bit with heavy write-intensive applications such as IoT or sensor data or social media data, because the B-tree data structures that drive or power these relational databases slows down due to their nature of the random reads and random writes for the heavy write applications.
It's an inevitable part of a data engineer's job to work with a variety of data. You will need to work with standard formats like CSV, JSON, XML, but also you'll need to work with proprietary formats. And you will need to get data in different sources, whether it be relational databases, NoSQL, or big data repositories. You will need to work with data at rest, streaming data or data in motion, and you might not have the skills to work with all of these different types of data sources from day one. But you need to be able to learn as you go and pick up these skills required for the project to work with different data sets, different data formats, and different data sources.
When it comes to the data formats, log data, XML data, JSON, etc., each of them comes with their own challenges. For example, log data is extremely challenging because it's unstructured, and you may need to write your own custom tools to parse the data depending on what you want to look at. Whereas XML was widely popular like a decade ago, especially with the SOAP protocol of the web applications. However, soon the web developers and the corporations discovered that it can be resource intensive, especially memory, because it has both the starting and ending tags. So then JSON came into the picture. They got rid of the ending tags and they looked like a key value pairs, and it saved some resources, and it is now widely used as part of the RESTful APIs, and then even newer versions of the data formats such as Apache Avro were gaining a wide popularity because of the efficiency on how they store the data.
One particular situation where we were converting data from a DB2 database into a SQL Server database, and it was challenging because the way that each of those expect imports and exports to happen is a little bit different. The data was particularly challenging, and that's where a lot of your challenge might come from in these projects, is from the data itself. In this particular case, the data had a lot of different characters in it, so usually we're looking for a character we can use as a delimiter. Oftentimes that's comma delimited, so we can separate our fields using commas. But we also have to think about situations where we have data that has commas in it. How do we properly separate that data? How do we properly define our fields? And in this particular case, we had to use different separators for different tables because every single special character that we could think of was in one of those tables. And the special characters that weren't were sometimes ones we couldn't use for separation, such as the bell character.
Welcome to the Understanding Data Lesson Summary video. Data is the foundation of data science. To be a successful data scientist, you must understand data in different forms, whether structured, semi-structured, or unstructured. In the videos and readings in this lesson, you explored how data can be generated, stored, and accessed. For data to be useful, it must be interpreted to derive meaning. Structured data has a well-defined structure or adheres to a specified data model. Can be stored in well-defined schemas such as databases, and in many cases, can be represented in multiple tables with rows and columns. The schema defines the relationship between the tables. Semi-structured has some organizational properties, but lacks a fixed or rigid schema. It cannot be stored in rows and columns. It contains tags and elements or metadata, which is used to organize data in hierarchy. The metadata provides useful information about this data. Metadata can be categorized as technical, process, or business. Metadata also needs managing to ensure information access and integration from various sources and appropriately shared across an organization, usually in a data catalog. A well-implemented data catalog enhances data discovery, repeatability, governance, and access. Unstructured data is heterogeneous. It comes from a broad range of sources and has a variety of business intelligence and analytics applications. Analyzing unstructured data often requires artificial intelligence to gain insights from it. It is important to know that the data for analysis can be stored from anything with an electronic footprint, whether it's generated and stored automatically or through manual efforts. While older records may exist in analog formats like paper, they typically require conversion to electronic formats for effective mining and processing. Typically, organizations use internal applications to support their day-to-day management of business activities and workflows. You can use data stored in databases and data warehouses as a source for analysis. You can also find publicly and privately held datasets for analysis. You can even purchase proprietary datasets. These datasets are usually made available as a single flat file such as CSV format or spreadsheets. For a number of years, flat files stored information about their structure in a format called XML. More recently, you see text data exchanged in JSON format, a straightforward format readable by humans and machines. JSON data does not have a predefined schema, so you can easily transfer it between data structures as they evolve. You can usually access the data in modern cloud-based software applications through an application programming interface or API. When dealing with JSON data, applications use what is called a RESTful API for data transfer. Many data providers and websites provide APIs for accessing their data. Twitter and Facebook both provide APIs to source data from posts for performing tasks such as opinion mining. This allows you to analyze sentiments on a given subject, such as customer satisfaction. Usually, data gathering and management are typically assigned to data engineers, although, as a data scientist, you most often need to transfer data for analysis. This process demands flexibility. As a data scientist, you will frequently work with extensive data sets, sometimes reaching terabytes in size. These continually updating massive data sets stem from sources like IoT applications, sensor data, and the constant influx of social media data collected from millions of users. Data scientists have a unique relationship with data. You specialize in data, so you must understand it intimately. But before you can analyze it, you'll need to know the modern-day ecosystem for organizing, storing, manipulating, and retrieving data. This lesson introduced you to some of these ideas.
A data repository is a general term used to refer to data that has been collected, organized, and isolated so that it can be used for business operations or mined for reporting and data analysis. It can be a small or large database infrastructure with one or more databases that collect, manage, and store datasets. In this video, we will provide an overview of the different types of repositories your data might reside in, such as databases, data warehouses, and big data stores, and examine them in greater detail in further videos. Let's begin with databases. A database is a collection of data or information designed for the input, storage, search and retrieval, and modification of data. And a database management system, or DBMS, is a set of programs that creates and maintains the database. It allows you to store, modify, and extract information from the database using a function called querying. For example, if you want to find customers who have been inactive for 6 months or more, using the querying function, the database management system will retrieve data of all customers from the database that have been inactive for 6 months or more. Even though a database and DBMS mean different things, the terms are often used interchangeably. There are different types of databases. Several factors influence the choice of database, such as the data type and structure, querying mechanisms, latency requirements, transaction speeds, and intended use of the data. It's important to mention two main types of databases here: relational and non-relational databases. Relational databases, also referred to as RDBMSs, build on the organizational principles of flat files, with data organized into a tabular format with rows and columns following a well-defined structure and schema. However, unlike flat files, RDBMSs are optimized for data operations and querying involving many tables and much larger data volumes. Structured Query Language, or SQL, is the standard querying language for relational databases. Then we have non-relational databases, also known as NoSQL, or Not Only SQL. Non-relational databases emerged in response to the volume, diversity, and speed at which data is being generated today, mainly influenced by advances in cloud computing, the Internet of Things, and social media proliferation. Built for speed, flexibility, and scale, non-relational databases made it possible to store data in a schemaless or free-form fashion. NoSQL is widely used for processing big data. A data warehouse works as a central repository that merges information coming from disparate sources and consolidates it through the extract, transform, and load process, also known as the ETL process, into one comprehensive database for analytics and business intelligence. At a very high level, the ETL process helps you to extract data from the different data sources, transform the data into a clean and usable state, and load the data into the enterprise's data repository. Related to data warehouses are the concepts of data marts and data lakes, which we will cover later. Data marts and data warehouses have historically been relational, since much of the traditional enterprise data has resided in RDBMSs. However, with the emergence of NoSQL technologies and new sources of data, non-relational data repositories are also now being used for data warehousing. Another category of data repositories are big data stores that include distributed computational and storage infrastructure to store, scale, and process very large data sets. Overall, data repositories help to isolate data and make reporting and analytics more efficient and credible while also serving as a data archive. A relational database is a collection of data organized into a table structure, where the tables can be linked or related based on data common to each. Tables are made of rows and columns, where rows are the records and the columns the attributes. Let's take the example of a customer table that maintains data about each customer in a company. The columns or attributes in the customer table are the customer ID, customer name, customer address, and customer primary phone, and each row is a customer record. Now, let's understand what we mean by tables being linked or related based on data common to each. Along with the customer table, the company also maintains transaction tables that contain data describing multiple individual transactions pertaining to each customer. The columns for the transaction table might include the transaction date, customer ID, transaction amount, and payment method. The customer table and transaction tables can be related based on the common customer ID field. You can query the customer table to produce reports such as a customer statement that consolidates all transactions in a given period. This capability of relating tables based on common data enables you to retrieve an entirely new table from data in one or more tables with a single query. It also allows you to understand the relationships among all available data and gain new insights for making better decisions. Relational databases use Structured Query Language, or SQL, for querying data. We'll learn more about SQL later in this course. Relational databases build on the organizational principles of flat files, such as spreadsheets, with data organized into rows and columns following a well-defined structure and schema. But this is where the similarity ends. Relational databases, by design, are ideal for the optimized storage, retrieval, and processing of data for large volumes of data, unlike spreadsheets that have a limited number of rows and columns. Each table in a relational database has a unique set of rows and columns, and relationships can be defined between tables, which minimizes data redundancy. Moreover, you can restrict database fields to specific data types and values, which minimizes irregularities and leads to greater consistency and data integrity. Relational databases use SQL for querying data, which gives you the advantage of processing millions of records and retrieving large amounts of data in a matter of seconds. Moreover, the security architecture of relational databases provides controlled access to data and also ensures that the standards and policies for governing data can be enforced. Relational databases range from small desktop systems to massive cloud-based systems. They can be either open source and internally supported, open source with commercial support, or commercial closed source systems. IBM DB2, Microsoft SQL Server, MySQL, Oracle Database, and PostgreSQL are some of the popular relational databases. Cloud-based relational databases, also referred to as database as a service, are gaining wide use as they have access to the limitless compute and storage capabilities offered by the cloud. Some of the popular cloud relational databases include Amazon Relational Database Service, or RDS, Google Cloud SQL, IBM DB2 on Cloud, Oracle Cloud, and SQL Azure. RDBMS is a mature and well-documented technology, making it easy to learn and find qualified talent. One of the most significant advantages of the relational database approach is its ability to create meaningful information by joining tables. Some of its other advantages include flexibility. Using SQL, you can add new columns, add new tables, rename relations, and make other changes while the database is running and queries are happening. Reduced redundancy. Relational databases minimize data redundancy. For example, the information of a customer appears in a single entry in the customer table, and the transaction table pertaining to the customer stores a link to the customer table. Ease of backup and disaster recovery. Relational databases offer easy export and import options, making backup and restore easy. Exports can happen while the database is running, making restore on failure easy. Cloud-based relational databases do continuous mirroring, which means the loss of data on restore can be measured in seconds or less. ACID compliance. ACID stands for atomicity, consistency, isolation, and durability. ACID compliance implies that the data in the database remains accurate and consistent despite failures, and database transactions are processed reliably. Now we'll look at some use cases for relational databases. Online transaction processing. OLTP applications are focused on transaction-oriented tasks that run at high rates. Relational databases are well suited for OLTP applications because they can accommodate a large number of users. They support the ability to insert, update, or delete small amounts of data. And they also support frequent queries and updates as well as fast response times. Data warehouses. In a data warehousing environment, relational databases can be optimized for online analytical processing, or OLAP, where historical data is analyzed for business intelligence. IoT solutions. Internet of Things, or IoT solutions, require speed as well as the ability to collect and process data from edge devices, which need a lightweight database solution. This brings us to the limitations of RDBMS. RDBMS does not work well with semi-structured or unstructured data, and is therefore not suitable for extensive analytics on such data. For migration between two RDBMSs, schemas and type of data need to be identical between the source and destination tables. Relational databases have a limit on the length of data fields, which means If you try to enter more information into a field than it can accommodate, the information will not be stored. Despite the limitations and the evolution of data in these times of big data, cloud computing, IoT devices, and social media, RDBMS continues to be the predominant technology for working with structured data. NoSQL, which stands for Not Only SQL, or sometimes non-SQL, is a non-relational database design that provides flexible schemas for the storage and retrieval of data. NoSQL databases have existed for many years, but have only recently become more popular in the era of cloud, big data, and high-volume web and mobile applications. They are chosen today for their attributes around scale, performance, and ease of use. It's important to emphasize that the No in NoSQL is an abbreviation for not only, and not the actual word no. NoSQL databases are built for specific data models and have flexible schemas that allow programmers to create and manage modern applications. They do not use a traditional row, column, table database design with fixed schemas, and typically not use the structured query language, or SQL, to query data, although some may support SQL or SQL-like interfaces. NoSQL allows data to be stored in a schemaless or free-form fashion. Any data, be it structured, semi-structured, or unstructured, can be stored in any record. Based on the model being used for storing data, there are 4 common types of NoSQL databases: key-value store, document-based, column-based, and graph-based. Key-value store. Data in a key-value database is stored as a collection of key-value pairs. The key represents an attribute of the data and is a unique identifier. Both keys and values can be anything from simple integers or strings to complex JSON documents. Key-value stores are great for storing user session data and user preferences, making real-time recommendations and targeted advertising, and in-memory data caching. However, if you want to be able to query the data on specific data value, need relationships between data values, or need to have multiple unique keys, a key-value store may not be the best fit. Redis, Memcached, and DynamoDB are some well-known examples in this category. Document-based. Document databases store each record and its associated data within a single document. They enable flexible indexing, powerful ad hoc queries, and analytics over collections of documents. Document databases are preferable for e-commerce platforms, medical records storage, CRM platforms, and analytics platforms. However, if you're looking to run complex search queries and multi-operation transactions, a document-based database may not be the best option for you. MongoDB, DocumentDB, CouchDB, and Cloudant are some of the popular document-based databases. Column-based. Column-based models store data in cells grouped as columns of data instead of rows. A logical grouping of columns, that is, columns that are usually accessed together, is called a column family. For example, a customer's name and profile information will most likely be accessed together, but not their purchase history. So, customer name and profile information data can be grouped into a column family. Since column databases store all cells corresponding to a column as a continuous disk entry, accessing and searching the data becomes very fast. Column databases can be great for systems that require heavy write requests, storing time series data, weather data, and IoT data. But if you need to use complex queries or change your querying patterns frequently, this may not be the best option for you. The most popular column databases are Cassandra and HBase. Graph-based. Graph-based databases use a graphical model to represent and store data. They are particularly useful for visualizing, analyzing, and finding connections between different pieces of data. The circles are nodes, and they contain the data. The arrows represent relationships. Graph databases are an excellent choice for working with connected data, which is data that contains lots of interconnected relationships. Graph databases are great for social networks, real-time product recommendations, network diagrams, fraud detection, and access management. But if you want to process high volumes of transactions, it may not be the best choice for you, because graph databases are not optimized for large volume analytics queries. Neo4j and Cosmos DB are some of the more popular graph databases. NoSQL was created in response to the limitations of traditional relational database technology. The primary advantage of NoSQL is its ability to handle large volumes of structured, semi-structured, and unstructured data. Some of its other advantages include the ability to run as distributed systems scaled across multiple data centers, which enables them to take advantage of cloud computing infrastructure, an efficient and cost-effective scale-out architecture that provides additional capacity and performance with the addition of new nodes, and simpler design, better control over availability, and improved scalability that enables you to be more agile, more flexible, and to iterate more quickly. To summarize the key differences between relational and non-relational databases, RDBMS schemas rigidly define how all data inserted into the database must be typed and composed, whereas NoSQL databases can be schema agnostic, allowing unstructured and semi-structured data to be stored and manipulated. Maintaining high-end commercial relational database management systems is expensive, whereas NoSQL databases are specifically designed for low-cost commodity hardware. Relational databases, unlike most NoSQL, support ACID compliance, which ensures reliability of transactions and crash recovery. RDBMS is a mature and well-documented technology, which means the risks are more or less perceivable as compared to NoSQL, which is a relatively newer technology. Nonetheless, NoSQL databases are here to stay and are increasingly being used for mission-critical applications. Earlier in the course, we examined databases, data warehouses, and big data stores. Now we'll go a little deeper in our exploration of data warehouses, data marts, and data lakes, and also learn about the ETL process and data pipelines. A data warehouse works like a multi-purpose storage for different use cases. By the time data comes into the warehouse, it has already been modeled and structured for a specific purpose, meaning it is analysis ready. As an organization, you would opt for a data warehouse when you have massive amounts of data from your operational systems that need to be readily available for reporting and analysis. Data warehouses serve as the single source of truth, storing current and historical data that has been cleansed, conformed, and categorized. A data warehouse is a multi-purpose enabler of operational and performance analytics. A data mart is a subsection of the data warehouse, built specifically for a particular business function, purpose, or community of users. The idea is to provide stakeholders data that is most relevant to them when they need it. For example, the sales or finance teams accessing data for their quarterly reports and projections. Since a data mart offers analytical capabilities for a restricted area of the data warehouse, it offers isolated security and isolated performance. The most important role of a data mart is business-specific reporting and analytics. A data lake is a storage repository that can store large amounts of structured, semi-structured, and unstructured data in their native format, classified and tagged with metadata. So, while a data warehouse stores data processed for a specific need, a data lake is a pool of raw data where each data element is given a unique identifier and is tagged with meta tags for further use. You would opt for a data lake if you generate or have access to large volumes of data on an ongoing basis, but don't want to be restricted to specific or predefined use cases. Unlike data warehouses, a data lake would retain all source data without any exclusions. And the data could include all types of data sources and types. Data lakes are sometimes also used as a staging area of a data warehouse. The most important role of a data lake is in predictive and advanced analytics. Now we come to the process that is at the heart of gaining value from data, the extract, transform, and load process, or ETL. ETL is how raw data is converted into analysis-ready data. It is an automated process in which you gather raw data from identified sources, extract the information that aligns with your reporting and analysis needs, clean, standardize, and transform that data into a format that is usable in the context of your organization, and load it into a data repository. While ETL is a generic process, the actual job can be very different in usage, utility, and complexity. Extract is the step where data from source locations is collected for transformation. Data extraction could be through batch processing, meaning source data is moved in large chunks from the source to the target system at scheduled intervals. Tools for batch processing include Stitch and Blendo. Stream processing, which means source data is pulled in real time from the source and transformed while it is in transit and before it is loaded into the data repository. Tools for stream processing include Apache Samza, Apache Storm, and Apache Kafka. Transform involves the execution of rules and functions that convert raw data into data that can be used for analysis. For example, making date formats and units of measurement consistent across all source data, removing duplicate data, filtering out data that you do not need, enriching data, for example, splitting full name to first, middle, and last names, establishing key relationships across tables, applying business rules and data validations. Load is the step where processed data is transported to a destination system or data repository. It could be initial loading, that is, populating all the data in the repository. Incremental loading, that is, applying ongoing updates and modifications as needed periodically. Or full refresh, that is, erasing contents of one or more tables and reloading with fresh data. Load verification, which includes data checks for missing or null values, server performance, and monitoring load failures, are important because of this process step. It is vital to keep an eye on load failures and ensure the right recovery mechanisms are in place. ETL has historically been used for batch workloads on a large scale. However, with the emergence of streaming ETL tools, they are increasingly being used for real-time streaming event data as well. It's common to see the terms ETL and data pipelines used interchangeably, and although both move data from source to destination, data pipeline is a broader term that encompasses the entire journey of moving data from one system to another, of which ETL is a subset. Data pipelines can be architected for batch processing, for streaming data, and a combination of batch and streaming data. In the case of streaming data, data processing or transformation happens in a continuous flow. This is particularly useful for data that needs constant updating, such as data from a sensor monitoring traffic. A data pipeline is a high-performing system that supports both long-running batch queries and smaller interactive queries. The destination for a data pipeline is typically a data lake, although the data may also be loaded to different target destinations, such as another application or a visualization tool. There are a number of data pipeline solutions available, most popular among them being Apache Beam and Dataflow. In this video, we will listen to several data professionals talk about some of the factors they consider while deciding on the most appropriate data repository for their organization.
So there's a number of factors to keep in mind while picking the right database for the job. You need to look at the use case. What is the data repository going to be used for? Is it going to be used for storing structured information, semi-structured or unstructured information? Or do you know beforehand what the schema of the data is? Is there performance requirements? Are you working with data at rest or streaming data or data in motion? Does the data need to be encrypted? What's the volume of data that you're working with? Do you need a big data system? And what are the storage requirements? Does the data need to be updated frequently and accessed frequently? Does it just need to be stored and kept in a vault for a long time and is needed for backup purposes, for example? And then your organization might have certain standards that might have put in place of which databases or which data repositories you're allowed to use for different kinds of tasks. So all of these factors need to be kept in mind.
So when we consider what data repository we want to choose, we look at these factors. We look at what are the kind of capacities that this data repository is supposed to handle. And then we also look at the type of access that we need this for. Do we access it in short intervals or do we run long-running queries on it? Am I using it more for transaction processing or am I using it for analytics or archival purpose or for data warehousing purpose? We also look for compatibility. How compatible this new data repository is with my existing ecosystem of programming languages, tools, and any processes that we have. We also consider the security features this repository gives us. And the most important thing is scalability. We may be happy with its performance today, but is it scalable enough? Can it scale along with the organization?
I don't often get to choose the type of data repository that my organization uses, and very few organizations use one data repository these days. On my team that I work on these days, we have a set of preferred solutions. We have a preferred enterprise relational database. We have a preferred open source relational database for some of the smaller projects and for the microservices. And then we also have a preferred unstructured data source. So those are our three main ones. The important thing is to think about the skills that you have within your organization or that you want to foster within your organization, and consider the costs of the various solutions. In our case, we have some experts on DB2, so our enterprise database of choice is DB2. However, there are other projects that use different ones. For open source, we've changed that a couple of times. We've gone a couple of different directions with where we really want to be there. And all of these, the hosting platform makes a difference as well, because now it's not just, do I want to use IBM DB2 or do I want to use some other vendor's Microsoft SQL Server or whatever. It's not between those two choices. It's when I do those, do I want to do them on AWS RDS? Maybe I should consider Amazon's Aurora. Maybe I should consider Google's relational offerings. There's so many different choices there that you have to consider. There's the decision of how should the data be stored. There's the decision of how should the data be retrieved. And there's also the decision of where. Those are all very important questions when you're deciding on data storage.
I would say the structure of the data, the nature of the application, and the volume at which the data is getting ingested into your database, all these factors determine the nature of the data source that you should pick. In most cases, a relational database should be enough. However, there will be edge cases where relational databases such as IBM DB2, Oracle, or Postgres won't necessarily do the job for you. In those cases, so depending on the use case, for example, if you're ingesting like gigabytes or terabytes of data per day, then document stores such as MongoDB or wide column stores such as Cassandra might be a good fit for you. At the same time, if you're trying to build a product recommendation engines or trying to show the network of relationships between different people on the social media, then graph data structures such as Neo4j or Apache Tinkerpop would be an ideal fit for you. At the same time, if you're mining through terabytes or petabytes of data for analytics, Hadoop engine with MapReduce would be a good fit for you. So it really boils down to the nature of the application and the volume of the data and the structure of the data before you can pick the right database or data source for your use case.
Gartner defines data integration as a discipline comprising the practices, architectural techniques, and tools that allow organizations to ingest, transform, combine, and provision data across various data types. The report further explains that data integration has several usage scenarios, such as data consistency across applications, master data management, data sharing between enterprises, and data migration and consolidation. In the field of analytics and data science, data integration includes accessing, queuing, or extracting data from operational systems, transforming and merging extracted data either logically or physically, data quality and governance, and delivering data through an integrated approach for analytics purposes. For example, to make customer data available for analytics, you would need to extract individual customers' information from operational systems such as sales, marketing, and finance. You would then need to provide a unified view of the combined data so that your users can access, query, and manipulate this data from a single interface to derive statistics, analytics, and visualizations. How does a data integration platform relate to ETL and data pipelines? While data integration combines disparate data into a unified view of the data, a data pipeline covers the entire data movement journey from source to destination systems. In that sense, you can use a data pipeline to perform data integration, while ETL is a process within data integration. There is no one approach to data integration. However, modern data integration solutions typically support the following capabilities: an extensive catalog of pre-built connectors and adapters that help you connect and build integration flows with a wide variety of data sources such as databases, flat files, social media data, APIs, CRM, and ERP applications. Open source architecture that provides greater flexibility and avoids vendor lock-in. Optimization for both batch processing of large-scale data and continuous data streams, or both. Integration with big data sources. Support for big data is increasingly driving the decision regarding choice of integration platforms. Additional functionalities. For example, specific demands around data quality and governance, compliance, and security. Portability, which ensures that as businesses move to cloud models, they should be able to run their data integration platforms anywhere, and data integration tools are able to work natively in a single cloud, multi-cloud, or hybrid cloud environment. There are many data integration platforms and tools available in the market, ranging from commercial off-the-shelf tools to open-source frameworks. IBM offers a host of data integration tools targeting a range of enterprise integration scenarios, such as InfoSphere Information Server, Cloud Pak for data, IBM Cloud Pak for integration, IBM Data Replication, IBM Data Virtualization Manager, IBM InfoSphere Information Server on Cloud, and IBM InfoSphere Data Stage. Talon's data integration tools include Talon Data Fabric, Talent Cloud, Talend Data Catalog, Talend Data Management, Talend Big Data, Talend Data Services, and Talend Open Studio. SAP, Oracle, Denodo, SAS, Microsoft, Kulik, and Tibco are some of the other vendors that offer data integration tools and platforms. Examples of open source frameworks include Dell Boomi, Jitterbit, and SnapLogic. There are a significant number of vendors who are offering cloud-based integration platform as a service, or iPaaS, as a hosted service via virtual private cloud or hybrid cloud, such as the Adeptia Integration Suite, Google Cloud's Cooperation 534, IBM's Application Integration Suite on Cloud, and Informatica's Integration Cloud. The data integration space continues to evolve as businesses embrace newer technologies and as data grows, be it in the variety of sources or its use in business decision-making.
Welcome to the Data Literacy Lesson Summary. As a data scientist, you need an awareness of data storage, possibilities for its organization and management, and options for retrieval. These systems enable you to find and analyze the data you need to make great discoveries hidden in that data. In this video, we'll summarize what you learned in this lesson about the technologies and tools to handle large amounts of data. Let's consider data repositories. These repositories need the ability to find the data you want and return it to you in a usable format. Your data type helps determine the type of repository you need. You can store structured, semi-structured, or unstructured data. Depending on the organization, you may need a relational or NoSQL database. For big data stores, your needs may call for a data warehouse, a data mart, or a data lake. Relational databases store structured data. These are the oldest types of repositories. The most conventional and frequently used relational database management systems, often abbreviated as RDBMSs, are based on the foundational concept of structuring data in a tabular format with data arranged in rows and columns. Each table usually relates to a topic, and the columns of data in the table contain a specific type of information related to that topic. Then, the database contains a defined schema that describes the table to each other. Relational databases usually rely on structured query language, or SQL, to search for and retrieve the data you need. You use SQL to manipulate the data. Relational databases are beneficial for visualizing, analyzing, and finding connections between different pieces of data. You link tables together by creating schemas. You can restrict database fields to specific data types and values, which minimizes irregularities and leads to greater consistency and data integrity. They offer easy export and import options, making backup and restoration easy. However, RBMSs do not work well with semi-structured or unstructured data. They are also slow to query with enormous data sets. Since RDBMSs use predefined structures for data to reside in, it becomes problematic when the data evolves and no longer conforms to that structure. Relational databases also limit field length, which means that sometimes they cannot accommodate the information you need. Because of these limitations and the quantities and diversity of data collected, many organizations have turned to not only SQL databases, or NoSQL for short. Built for speed, flexibility, and scale, non-relational databases allow storing data without stringent schemas. They can house semi-structured and unstructured data. NoSQL databases include document-based, key-value, columnar, and graph. Document-based databases store semi-structured documents such as JSON files. You group documents into collections, and each document has its structure. Key value stores each piece of data as a key-value pair, so you retrieve and update the data using the key. Columnar databases store data in columns rather than rows, enabling storage of large volumes of data suitable for analytical workloads. Graph databases store data in nodes. Nodes have relationships and properties and can manage and query complex relationships between them. You can use technologies such as data warehouses, data marts, and data lakes for high volumes of data. A data warehouse works like a multi-purpose storage for different use cases. The data has already been modeled and structured for a specific purpose. As an organization, you would opt for a data warehouse when you have a massive amount of data from your operational systems that must be readily available for reporting and analysis, A data mart is a subsection of the data warehouse built specifically for a particular business function, purpose, or community of users. A data mart offers analytical capabilities for a restricted data warehouse area, offering isolated security and performance. A data lake is a storage repository that can store large amounts of structured, semi-structured, and unstructured data in their native format, classified and tagged with metadata. Let's review storage options. Data pipelines address an organization's need to collect, transform, and move data. Data pipelines have multiple steps, providing a systematic process to handle massive amounts of data as it is continually collected, processed, and made available. ETL, which stands for extract, transform, and load, is a subset of a data pipeline, referring to an automated process where an organization converts its raw data into data ready for analysis. So now, as a future data scientist, you are aware of many technologies needed to handle big data before analysis can begin. These include data storage, organization and management, and retrieval. Data storage options depend on the type of data, its volume, and how you intend to organize it. Using a data pipeline such as ETL provides a process to manage and retrieve the data so you can analyze it as a data scientist.